Have you ever looked up at the night sky and felt a sense of awe, wondering just how much we still don't understand about the cosmos? Out there, beyond the familiar glow of stars and planets, lies a universe filled with mysteries so profound they challenge the very foundation of what we think we know. From dark energy accelerating the expansion of space to black holes that warp time itself, our galaxy, and the universe beyond is home to phenomena that even the most brilliant minds in astrophysics struggle to explain. These aren't just scientific curiosities, they're cosmic puzzles that force us to rethink reality as we know it. Today, we're embarking on a journey to explore 30 of the most extraordinary galactic phenomena that defy explanation. We'll venture into regions of space where the laws of physics seem to break down, where light behaves in ways we can't predict, and where invisible forces shape the fate of entire galaxies. This isn't just a tour of strange cosmic sights. It's an invitation to join in the wonder and mystery that astronomers and physicists grapple with every day. You'll come away with a deeper appreciation for just how strange, beautiful, and utterly baffling our universe can be. So settle in and get ready to explore the edges of human knowledge. We're about to dive into phenomena that challenge our understanding of matter, energy, and the very fabric of space and time. Whether you're a seasoned space enthusiast or just curious about the wonders of the cosmos, this journey will leave you with a sense of awe and maybe even a few questions of your own. Let's begin. Our journey into the unknown begins close to home, relatively speaking, with a force so immense it is tugging our entire galaxy and every one of our cosmic neighbors on a relentless journey we cannot stop. Imagine you're drifting in a vast cosmic river, moving with a current you can't see or fully comprehend. That is our reality. Our Milky Way, along with the entire local group of galaxies, is being pulled through space at an astonishing 14 million miles per hour toward a mysterious, invisible point in the cosmos known as the Great Attractor. This isn't just a gentle nudge, it's a powerful, unavoidable pull that has shaped the motion of galaxies for billions of years, the most frustrating part. We can't even get a clear look at it. The Great Attractor lies in a region of the sky astronomers call the zone of avoidance. This isn't a sci-fi danger zone. It's a vast swath of our view that is obscured by the dense dust and stars of the Milky Way's own galactic plane. It's like trying to peer through a thick, dusty curtain at a spectacular show happening just on the other side. For decades, this cosmic veil has hidden the true nature of the Great Attractor, forcing scientists to literally look around the obstruction, using instruments that can see through interstellar dust like infrared and radio telescopes to map the gravitational influence of what lies beyond. So what could possibly possess enough gravitational might to command the motion of hundreds of galaxies? The leading theory points to an unimaginably massive concentration of dark matter, the mysterious, invisible stuff that makes up the majority of the universe's mass. This hidden structure, potentially a supercluster of galaxies far denser than our own, could be the engine behind this great pull, but some data suggests even that might not be enough. The sheer scale of the force has led to more exotic proposals, including the influence of even larger structures beyond it, like the Shapley supercluster, which might be pulling on the Great Attractor itself, creating a complex cosmic tug of war we are only beginning to map. The true identity of the Great Attractor remains one of the most humbling mysteries in astronomy. It serves as a powerful reminder that even the grand motion of our galaxy is not entirely our own, but is dictated by forces hidden in the darkness, reminding us that we are participants in a cosmic dance whose steps we are still struggling to learn. And as we contemplate the immense, unseen force pulling our galaxy, we are immediately confronted with the most significant source of that gravitational power itself. The Great Attractor is likely a massive knot of dark matter, the single most baffling and dominant ingredient in our entire cosmic recipe. Think of everything you can see around you, every person, every planet, every star blazing in the night sky. All of that, every bit of normal matter that makes up our known universe, accounts for less than 5% of the total cosmos. Dark energy makes up about 68%, and the remaining 27%, over a quarter of everything that exists, is dark matter. It is the invisible skeleton upon which the universe is built, and we have absolutely no idea what it is. We cannot see it, touch it, or detect it directly because by its very nature, it does not interact with light or electromagnetic radiation at all. It neither emits, absorbs, nor reflects any form of light, making it completely transparent and invisible to our telescopes. So how do we even know it's there? We observe its profound gravitational effects. The rotation of galaxies provides the clearest evidence. Stars on the outer edges of spiral galaxies orbit at speeds that should be impossible. According to the laws of gravity and the amount of visible mass we can see, those distant stars should be flung off into the void, much like a ball on a string would fly away if you spun it too fast. The fact that they don't means there must be an enormous amount of unseen mass, a vast halo of dark matter, surrounding each galaxy, its gravity holding everything together. For decades, the leading theoretical candidate for dark matter has been a class of particles known as WIMP, or weakly interacting massive particles. These hypothetical particles would be heavy, slow-moving, and, as their name implies, interact with normal matter only through gravity and the weak nuclear force, making them extraordinarily difficult to catch. Physicists have built incredibly sensitive experiments deep underground in old mines and tunnels, places shielded from cosmic rays and other interference, all hoping to detect the minuscule vibration or flash of heat that would signal a WIMP bumping into an atom of normal matter. Yet, after years of searching with ever more sophisticated detectors, the results have been profoundly silent. Not a single confirmed WIMP has ever been detected. This persistent lack of evidence has forced a monumental and thrilling crisis in physics. It forces us to ask a terrifying and exciting question: are we wrong about dark matter, or are we wrong about the fundamental laws of the universe? Alternative theories are now gaining traction, from the possibility that dark matter is made of something even more exotic, like ultralight particles called actions, to the radical idea that we don't need dark matter at all, and that our understanding of gravity itself is incomplete on galactic scales. This isn't just a missing puzzle piece, it's a gaping hole in our model of reality, a silent, invisible majority that governs the fate of galaxies while remaining utterly elusive to our attempts to understand it. But if the gravitational grip of dark matter is the cosmic glue holding galaxies together, then its counterpart, dark energy, is the mysterious force actively working to tear the entire universe apart. Just a few decades ago, the prevailing scientific belief was that the universe's expansion, set in motion by the Big Bang, was gradually slowing down over time. The collective gravity of all matter was thought to be acting like a cosmic brake, pulling everything back together. The biggest question was whether that pull would be strong enough to eventually reverse the expansion in a big crunch, or if it would simply slow it to a near halt. Then, in the late 1990s, two separate teams of astronomers made a discovery so shocking it won them the Nobel Prize and completely upended our cosmic narrative. By observing distant supernovae as cosmic mile markers, they found that the universe's expansion isn't slowing down at all. It's accelerating. Galaxies are flying away from each other faster and faster as time goes on, as if some invisible repulsive force is steadily pushing on the fabric of space itself. That phantom force is what we now call dark energy. To grasp how bizarre this is, we have to revisit Einstein's theory of gravity. In our everyday experience, gravity is always attractive. It pulls things together. But dark energy appears to be a form of gravity that is repulsive. It's not pushing on objects themselves, but rather causing the very space between galaxies to stretch at an ever-increasing rate. Imagine you're blowing up a balloon with tiny dots on its surface. As you inflate it, the dots move apart. Now imagine the balloon starts inflating faster and faster all on its own, with no one blowing more air into it. That's the effect of dark energy on our universe. It makes up a staggering 68% of the total mass energy content of the cosmos, dwarfing both normal matter and dark matter, which means this mysterious repulsive force is the dominant component of reality. The leading theoretical explanation for dark energy comes from an idea Einstein himself proposed and later discarded: the cosmological constant. He introduced this mathematical fudge factor as a form of energy inherent to the vacuum of space itself to force his equations to describe a static universe, which was the belief at the time. When the universe was found to be expanding, he called it his biggest blunder. Ironically, it might be his greatest prediction. A cosmological constant would mean that empty space is not empty at all, but seething with a faint, constant energy density that exerts negative pressure, driving the acceleration we observe. The problem, and it is a colossal one, is the value of this energy. When physicists attempt to calculate the predicted strength of this vacuum energy using our best theories of quantum mechanics, they arrive at a number that is unimaginably large. But when astronomers measure the actual observed strength of dark energy's effect through the accelerating expansion, the value is incredibly small. How small? The predicted value is larger than the observed value by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. This discrepancy is not just a minor rounding error. It is the largest and most embarrassing gap between theory and observation in the entire history of science. We are off by more than a trillion orders of magnitude. This is known as the cosmological constant problem, and it suggests we are profoundly missing something fundamental about the nature of space, energy, or gravity itself. Other theories suggest dark energy might not be a constant after all, but a dynamic force field that has changed over the life of the universe, an idea sometimes called quintessence. Or perhaps our understanding of gravity on the largest cosmic scales is simply wrong and needs a complete overhaul, much like Newton's laws were refined by Einstein. What makes dark energy so deeply unsettling is that it determines the ultimate fate of everything. If it continues to accelerate the expansion indefinitely, it points toward a cold, lonely end for the cosmos, where distant galaxies eventually fade from view, leaving any future observers in an island universe surrounded by an ever-growing void of nothingness. Yet while dark energy works on the largest possible scales to push the universe apart, another mystery of immense power is at work right here in our own galactic backyard, shaping structures so vast they redefine our understanding of our home galaxy's violent history. Extending from the very heart of the Milky Way like two colossal, silent ghosts are the Fermi Bubbles. These are not made of gas or dust in any normal sense. They are enormous, symmetrical lobes of incredibly high energy radiation, primarily gamma rays, that stretch for 25,000 light-years above and below the galactic plane. To put that impossible scale into perspective, our entire solar system is a mere speck, only about 1,000th of that distance from the galactic center. If our eyes could see in gamma rays, these structures would dominate the night sky, each bubble appearing 26 times wider than the full moon. Their discovery was a complete accident, a stunning revelation hidden in plain sight. It wasn't until 2010, when scientists were painstakingly analyzing data from the Fermi Gamma Ray Space Telescope, that these faint but gigantic outlines emerged from the background noise of the universe. The find was so unexpected it sent astrophysicists scrambling for explanations. What cosmic event could possibly have unleashed such a titanic amount of energy, carving out and inflating these perfect, hourglass-shaped structures that stand as monuments to a cataclysm we somehow missed? The prime suspect immediately became the supermassive black hole at the center of our galaxy, Sagittarius, a star. We know that black holes, especially supermassive ones, are not just passive vacuum cleaners. When they actively feed on surrounding matter, they can become the most powerful engines in the universe, converting gravitational energy into intense radiation and often firing out colossal jets of particles at near light speed from their poles. The leading theory suggests that several million years ago, Sagittarius, a star, might have had a large meal, perhaps a dense cloud of gas or even a star that ventured too close. This feeding frenzy could have triggered a massive, short-lived outburst, a jet of energetic material that punched directly up and down through the galaxy's disk, inflating these giant bubbles as it went. This would have been a brief but unimaginably violent event in our galaxy's history, a roar from a usually silent beast. However, not all the evidence neatly fits this black hole outburst theory. The bubbles have very well-defined edges and a surprisingly uniform brightness, which suggests they might have been formed by a more sustained, continuous energy release rather than a single, explosive burp from the black hole. This has led to a compelling alternative hypothesis, a period of frenzied star formation near the galactic center. In this scenario, not one, but hundreds or thousands of massive stars could have been born in a short period. These giant stars live fast and die young, exploding as supernova in rapid succession. The combined force of all these stellar explosions could have created a powerful, outgoing wind of energy and particles, essentially blowing a giant, spherical bubble in the galactic halo that was then squashed by external pressure into its current elongated shape. Both of these theories are compelling, yet both also face significant challenges. A black hole jet might struggle to create such symmetrical and evenly filled structures, while a starburst wind might not be powerful enough to account for the extreme high-energy gamma rays we observe. The true answer might even lie in a combination of both events, or perhaps something entirely different that we haven't yet considered. The Fermi Bubbles stand as a stark reminder that our galaxy has a violent and dynamic past, and that even the most massive structures, hidden in a wavelength of light invisible to our eyes, can go unnoticed until we have the right tools to see them. They are a recent and humbling discovery, proving that our own cosmic neighborhood still holds enormous secrets waiting to be uncovered. Yet while the Fermi Bubbles represent a colossal mystery written across the sky, our next phenomenon is a whisper from the void, a fleeting signal so perfect and so unexplained that it has become the stuff of legend. It was a warm August night in 1977, a time when the search for extraterrestrial intelligence was more a fringe pursuit than a mainstream science. An astronomer named Jerry Amon was volunteering for Ohio State University's Big Ear Radio Telescope project, sifting through reams of computer printout data from a scan of the sky days earlier. The system was designed to flag any narrowband radio signal, the kind predicted to be used for interstellar communication, that stood out significantly from the background noise of the universe. As his eyes scanned the long strings of alphanumeric codes, one particular sequence stopped him cold. The signal was so powerful, so perfectly matched to what they were looking for, that he circled it on the printout and simply wrote, "Wow." In the margin, that single, excited annotation gave the signal its enduring name, and it remains the most tantalizing, unexplained event in the history of the search for alien civilizations. The numbers themselves tell the story of its strangeness. The WOW signal was a strong, narrowband radio burst at precisely 1420 MHz. This frequency is part of a protected radio band called the hydrogen line, a quiet channel in the cosmic radio symphony that scientists have long theorized would be an ideal, natural choice for any civilization trying to announce its presence. The signal lasted for a full 72 seconds, the exact amount of time the Big Ear telescope could focus on any single point in the sky as the Earth rotated. It rose to an incredible intensity and then faded away perfectly, creating a signature that matched exactly what an artificial, extraterrestrial signal from a fixed point in space should look like. Nothing natural that we know of behaves in this way. Stars, pulsars, and quasars all emit broad-band radio noise across a wide range of frequencies. The WOW signal was a laser-like beam of radio energy, a perfect needle in a cosmic haystack. The immediate and obvious reaction was to try and hear it again. If an intelligent civilization was broadcasting, surely they wouldn't just say hello once and then go silent forever. Over the following decades, astronomers pointed countless radio telescopes, including the very powerful Allen telescope array built specifically for SETI, back toward that same precise spot in the constellation Sagittarius. They scanned for hours, days, and years. The result was an profound and enduring silence. The signal never repeated, not a trace. This single, brilliant flash is all we have, and its one-off nature is the core of the mystery. If it was a deliberate broadcast, why only once? If it was an accident, a fleeting burst of powerful radar or communication that happened to be pointed right at us, what could possibly explain its immense power? This lack of repetition has fueled a vigorous scientific debate for over 4 decades. The most persistent natural explanation points to a comet. In 2016, an astronomer proposed that the signal could have been caused by the hydrogen cloud surrounding 2 comets that happened to be passing through that exact region of space at that exact time. The idea is that the sun's light could cause these clouds to emit radiation at the right frequency. While it was a clever proposal, it was quickly dismantled by other scientists. The Big Ear telescope was not tuned to detect the specific kind of emission a hydrogen comet cloud would produce, and comets are not point-like sources. They would have created a much broader, messier signal, not the sharp, clean spike that was observed. The comet theory, while popular in the media, is widely rejected by most astronomers. Other theories range from a highly improbable series of reflections of a human-made signal bouncing off a piece of space debris to an entirely new and unknown astrophysical event. But the possibility that simply will not fade away is that the WOW signal was exactly what it looked like, a transient, unintentional beacon from a distant technology. Perhaps it was a powerful military radar sweep from an alien world, momentarily aimed in our direction, or the energy burst from a massive interstellar ship kicking into warp drive. Or a communication beam meant for a receiver elsewhere in the galaxy that we briefly drifted through. Its singular nature is both the most frustrating and most compelling thing about it. It is a clue without a crime, a message with only one character. It embodies the ultimate challenge of SETI. The universe is vast, time is long, and we might only get one chance to hear a hello. The WOW signal stands as a haunting reminder that we might have already heard that hello, but we were too slow to answer and the line has gone dead. But if the WOW signal was a whisper, then what astronomers began detecting in 2007 are cosmic screams, brief, violent, and immensely powerful blasts of energy that appear to come from the deepest reaches of intergalactic space. They are known as fast radio bursts, or FRB, and they represent one of the most explosive and least understood mysteries in modern astronomy. For just a few milliseconds, these events unleash a torrent of radio waves that can outshine entire galaxies, discharging more energy than our sun emits over 80 years, all in the blink of an eye. The first one was discovered almost by accident, hidden in archived data from the Parkes Radio Telescope in Australia. A single, startling spike in a chart that seemed to defy any logical explanation. For years, a handful of these one-off events were found, each one a solitary, brilliant flash in the cosmic dark that left astronomers with more questions than answers. The mystery took an even more bizarre turn in 2016 with the discovery of a repeater. Unlike the singular events that vanished without a trace, FRB 121022, as it's known, did something extraordinary. It flashed again. And then again. This was a monumental shift. It proved that whatever engine was powering these bursts, it wasn't necessarily destroyed in the process. Some FRBs could be cataclysmic, one-time events like the death throes of a star, while others were clearly driven by a persistent object capable of surviving multiple eruptions. This distinction immediately ruled out a whole class of theories and opened the door to others, turning FRBs from a mere curiosity into a central puzzle of high-energy astrophysics. Pinpointing the origin of these bursts became the next great challenge. Because radio waves travel through the sparse gas between galaxies, they get slightly spread out or dispersed. By measuring this dispersion, astronomers can estimate how much material the signal has traveled through, and therefore its approximate distance. The results were staggering. These signals were not coming from within our galaxy. They were arriving from billions of light-years away, meaning we are witnessing events that occurred when the universe was half its current age. The immense distance only deepens the enigma because for a signal to be that bright by the time it reaches us, the source must have been almost unimaginably powerful. So what in the universe could possibly create such a magnificent, fleeting burst? The hunt for an explanation has led to a spectrum of proposals, ranging from the well-grounded to the wildly speculative. On the more conventional end, the prime suspects are magnetars. These are a type of neutron star, the ultra-dense, collapsed core of a massive star, but with a terrifying twist. They possess the most powerful magnetic fields known to exist in the universe. A magnetar's magnetic field is so strong it could strip the information from a credit card from a distance halfway to the moon. The theory suggests that a starquake on the surface of a magnetar, a sudden cracking of its rigid crust under immense strain, could release a colossal flare of energy that we would detect as an FRB. This hypothesis gained significant credibility in 2020 when a known magnetar within our own Milky Way galaxy, named SGR 1935 plus 215, erupted. It produced a radio burst that, while 1,000 times less energetic than the extragalactic FRBs, shared nearly identical properties. It was the first undeniable proof that at least some FRBs are born from these magnetic monsters. But not every detected burst fits this pattern neatly. The repeating FRBs, for instance, show patterns and structures that are difficult to explain with a simple starquake model. Some repeat with an erratic cadence, while others have exhibited a startlingly regular periodicity, flaring up on a predictable schedule. This has led to other theories involving bizarre cosmic duos, like a neutron star in a highly elliptical orbit around a black hole. As the neutron star swings close to the black hole on each orbit, immense tidal forces could rip material from its surface, triggering a violent burst of energy at perihelion. And then, of course, there is the most speculative yet most captivating possibility: advanced alien civilizations. The notion is that the incredible energy and focused nature of these bursts could be signatures of technology, not natural phenomena. Perhaps they are power beams for immense light sails propelling interstellar ships, or accidental leakage from a planet-sized transmitter. While most astronomers consider this the least likely explanation, it remains a tantalizing, if remote, possibility that underscores just how perplexing these signals truly are. The recent detection of an FRB from within our own galaxy has not solved the mystery. It has instead given us a front-row seat to the phenomenon, allowing us to study its environment in unprecedented detail and confirming that magnetars are indeed one source. But with each new discovery, the story becomes more complex, not less. We now know that FRBs are not all the same. They are a diverse family of events with multiple potential parents. They are cosmic transients, brief and brilliant messengers from across the universe that challenge our understanding of physics under the most extreme conditions imaginable. But if FRBs are the universe's most powerful temporary radio beacons, then the process of galactic cannibalism is one of its most enduring and violent forms of construction, a slow-motion demolition and rebirth that shapes the very galaxies we see today. We often picture galaxies as isolated, serene islands in the void, but nothing could be further from the truth. They are dynamic and often ruthless structures, growing not just from the gentle accretion of gas, but through the violent consumption of their smaller neighbors. This process, known as galactic cannibalism, is a fundamental force in galactic evolution, and it presents us with a series of profound puzzles that challenge our simulations and our understanding of dark matter itself. Imagine a vast cosmic dance where the lead partners are giant spiral galaxies like our own Milky Way, and their smaller companions are dwarf galaxies. The dance is not a gentle waltz, but a destructive gravitational tango. As a dwarf galaxy is pulled into the overwhelming gravitational field of its larger neighbor, immense tidal forces begin to stretch and distort it. Stars are ripped from their orbits, and vast streams of stellar material are drawn out into long, elegant arcs that wrap around the cannibal galaxy like celestial ribbons. These stellar streams, the ghostly remnants of digested galaxies, can be seen around our own Milky Way and Andromeda, silent testimony to this ongoing feast. The most astonishing part of this violent process is not the destruction, but the paradoxical creation that often follows. One might assume that such a violent merger would leave the larger galaxy a mangled, chaotic wreck. Yet, time and again, we observe that these collisions can actually trigger the formation of beautiful, well-ordered spiral structures. The gravitational shockwaves from the merger can compress vast clouds of gas, igniting furious waves of new star birth and ultimately settling into the majestic spiral arms we recognize. This is where our cosmic simulations run into a serious problem, known as the missing satellite problem. When astrophysicists create incredibly detailed computer models of how galaxies form according to our standard cosmological model, which includes dark matter, they get a very specific prediction. The simulations show that the dark matter halo of a large galaxy like the Milky Way should be swarming with hundreds of small, dense clumps of dark matter. Each of these clumps should have enough gravity to pull in gas and form stars, meaning we should see hundreds of small dwarf galaxy companions orbiting our home. But when we look out into the sky, we only see a few dozen. It's a glaring discrepancy between what our theories predict and what we actually observe. Where are all these missing satellites? This isn't just a minor accounting error. It points to a potential flaw in our fundamental understanding of dark matter or galaxy formation. One leading solution proposes that our understanding of dark matter is correct, but our ability to see its smallest galaxies is not. The idea is that those hundreds of dark matter clumps did indeed form, but the vast majority were simply too small and faint to attract enough gas to create a significant number of stars. They would be made almost entirely of dark matter, making them virtually invisible to our telescopes. We may be surrounded by a vast, unseen swarm of these dark galaxies, their presence only detectable indirectly through their gravitational influence. Another, more radical explanation challenges the properties of dark matter itself. The standard model assumes cold dark matter, meaning the particles move relatively slowly. But what if dark matter is actually warmer, meaning the particles are lighter and faster? This warm dark matter would have suppressed the formation of the very smallest clumps in the early universe, resulting in far fewer dwarf galaxies from the start, a prediction that would neatly solve the missing satellite problem. However, this theory has its own set of challenges and is still a subject of intense debate. Beyond the missing satellites, these galactic mergers present another enigma: stability. The process of devouring a smaller galaxy should, in principle, inject a huge amount of chaotic energy into the larger galaxy's disk. The gravitational havoc should violently puff up the disk, randomizing stellar orbits and destroying any delicate spiral structure. Yet, we see that large spiral galaxies like our own have remained remarkably stable and thin-disked over billions of years, despite evidence that they have consumed numerous smaller galaxies. This suggests there is a mysterious stabilizing mechanism at work, a process we don't fully understand that allows galaxies to absorb these violent impacts and maintain their elegant structure. Some physicists point to the overwhelming gravitational influence of the dark matter halo itself, which may act as a stabilizing scaffold, absorbing the shock and preventing the visible disk from being torn apart. Others suggest that continuous, gentle accretion of fresh gas from intergalactic space helps to smooth out and settle the disk after a merger. The true answer remains elusive, highlighting that the simple act of a galaxy eating another galaxy is a complex cosmic event that we are still striving to fully comprehend. Yet, even as we map the violent history written in galactic mergers, we are forced to confront a discovery that cuts to the very core of cosmology, a finding so unsettling it was given a name straight out of a thriller, the axis of evil. This is not a malevolent force, but a mysterious and deeply unexpected pattern etched into the oldest light we can see, the cosmic microwave background. This faint afterglow is the remnant heat from the Big Bang, a snapshot of the infant universe when it was just 380,000 years old. For decades, this cosmic background radiation has been the cornerstone of our modern understanding of the universe, portraying a cosmos that is remarkably uniform and isotropic, meaning it should look the same in every direction with no special place or preferred axis. This assumption, known as the cosmological principle, is so fundamental that nearly all of modern cosmology rests upon it. The discovery of the axis of evil doesn't just challenge this principle, it seemingly throws a wrench into the entire machine. It all began with the incredibly detailed all-sky maps produced by satellites like WMAP and later Planck. As scientists analyzed the subtle temperature fluctuations in this ancient light, the tiny ripples that would eventually grow into galaxies and clusters, they noticed something that should be statistically impossible. The patterns of hot and cold spots, the very blueprint for all structure in the universe, appeared to be subtly aligned with the plane of our own solar system. It's as if the universe's grandest design has a faint watermark that somehow knows about the ecliptic, the imaginary flat disk on which Earth and the other planets orbit the Sun. This is profoundly weird. Why would the earliest moments of the entire universe bear any correlation whatsoever to the orientation of a single, average solar system that wouldn't even form for another 9 billion years? The chance of this happening randomly is astronomically low, suggesting that either we are seeing a ghost in the machine, a systematic error, or we are witnessing a genuine crack in our foundational theories. The implications are staggering. If this alignment is real, it suggests the universe has a preferred direction, a cosmic north that breaks the fundamental rule of isotropy. This would mean that our place in the cosmos is not average or typical after all, a direct violation of the Copernican principle, which is a key part of the broader cosmological principle. We would have to radically rethink our entire cosmic narrative. One of the most dramatic proposals is that this alignment is evidence that our galaxy resides inside a giant cosmic void, an immense bubble of lower than average density that is hundreds of millions of light years across. In this scenario, the void would act like a gravitational lens on a colossal scale, distorting the light from the cosmic microwave background as it travels to us and creating the illusion of an alignment. This would be a humbling realization, suggesting that our entire local volume of space is atypically empty, and that we have been making incorrect assumptions about the expansion rate and composition of the universe based on our biased viewpoint. Other theories are even more radical, suggesting that our understanding of the very first moments of the universe needs an overhaul. Perhaps the theory of cosmic inflation, the idea that the universe underwent a period of exponential expansion immediately after the Big Bang, is incomplete. Maybe inflation did not happen in the same way in all directions, leaving behind an anisotropic imprint on the fabric of spacetime itself. Or perhaps the alignment is a clue to something pre-Big Bang, a relic of a prior state of the cosmos that influenced the initial conditions of our own universe. The most cautious explanation, and the one many scientists still favor, is that the effect is not cosmological at all, but rather an artifact of our own measurement. The cosmic microwave background is incredibly faint, and teasing its signal from the foreground noise of our own galaxy is a Herculean task. It is possible that despite the best efforts of the teams behind WMAP and Planck, some subtle contamination from galactic dust or other local astrophysical phenomena is creating this illusory pattern. However, as each new analysis is performed and the data is cleaned with ever more sophisticated methods, the alignment stubbornly persists. It refuses to go away. The axis of evil remains one of the most profound and disquieting mysteries in cosmology. It is a statistical anomaly that whispers of a deeper truth we have not yet grasped, a hint that our universe might not be as uniform and featureless as we have long believed. It forces us to confront the uncomfortable possibility that we are not just passive observers of a perfectly isotropic cosmos, but that our local environment may be actively shaping our view of the whole, potentially leading us to draw grand conclusions from a perspective that is anything but typical. Yet as we grapple with the universe's grandest patterns and potential flaws in our most fundamental principles, we are drawn to a single, unassuming point of light over 1,000 light-years away that presents a mystery on a more intimate but no less baffling scale. In the constellation Cygnus, a star known as KIC 8462852, or more famously as Tabby's star, behaves in a way that absolutely nothing else in our catalogue of hundreds of thousands of stars does. Its story begins with the Kepler Space Telescope, a mission designed to find planets by staring tirelessly at stars, waiting for the telltale, periodic dimming that occurs when an orbiting planet passes in front of its sun. Most stars exhibit these predictable, gentle dips in brightness of 1% or less, repeating like clockwork every few days or weeks. Tabby's star did not play by these rules. Instead, Kepler recorded dips of absolutely staggering depth and bizarre irregularity. The star's light would plummet by up to 22%, a colossal amount that signifies something truly enormous is blocking its light. To put that in perspective, if a Jupiter-sized planet, the largest type we know, were to pass in front of this star, it would cause a dimming of only about 1%. These dips were not periodic either. They were erratic, asymmetric, and lasted for days or even weeks at a time. It was as if the star was being eclipsed by a vast, shapeless, and constantly changing swarm of objects, a pattern of shadow completely unlike the clean, repeating transit of any known planet. The initial and most natural explanation proposed was a massive cloud of comets. The idea was that a family of exocomets, perhaps disturbed by a nearby star, could have been breaking up and creating a huge, dusty debris field that occasionally passed in front of Tabby's star, causing the deep, irregular dimming. While this was a creative solution, it quickly ran into serious problems. To block that much light, the number of comets required would be almost implausibly vast, numbering in the hundreds of thousands or even millions. Furthermore, subsequent analysis of decades-old photographic plates revealed something even more astonishing. The star's overall brightness appears to have been gradually but significantly dimming over the past century. A swarm of comets might explain short-term dips, but it struggles to account for a century-long fading trend, a finding that, if confirmed, adds another layer of profound mystery. It was the sheer inadequacy of these natural explanations that led to the most famous and captivating hypothesis, alien megastructures. Specifically, the idea of a Dyson sphere, a hypothetical shell of solar collecting panels or habitats built by an advanced civilization around its star to harness nearly all of its energy output. A partially constructed or swarm-like Dyson sphere, made of countless individual orbiting collectors, could perfectly explain the irregular, deep dimming and the long-term decline in brightness. The hypothesis was never presented as the most likely scenario, but rather as a legitimate, last-resort idea that had to be considered when all known natural phenomena fell short. This catapulted Tabby's star, named after the astronomer Tabitha Boyajian who led its initial study, into international headlines and public imagination. This attention triggered one of the most extensive and passionate astronomical follow-up campaigns in history. When the star was seen dipping again in 2017, the global astronomical community sprang into action. Dozens of the world's largest telescopes, from the Keck Observatory in Hawaii to the Gran Telescopio Canarias in Spain, were pointed at it, collecting data across the entire electromagnetic spectrum. The results from this intense scrutiny were both illuminating and deeply puzzling. They revealed that the star dims more in blue light than in red light. This is a crucial clue because it means that whatever is blocking the light is not an opaque, solid object like a planet or a solid megastructure. Instead, it behaves like fine dust which scatters blue light more effectively than red. This finding seemed to deal a heavy blow to the solid megastructure idea and pointed firmly back towards a natural, dusty explanation. Yet the mystery is far from solved. While dust seems to be present, its origin and behavior remain completely unknown. What natural process could create such immense, erratic, and dynamic clouds of dust around a star that otherwise appears perfectly normal? The star is not young, where such violent dust-forming events are common, and it is not variable in a way that would explain this behavior. Every proposed model, from giant planet collisions to epic volcanic eruptions on a moon, feels like trying to force a square peg into a round hole. They might explain one aspect of the data, but they fail to create a cohesive picture that accounts for all of the star's bizarre antics. Years of monitoring have systematically eliminated the simple explanations, but a satisfying, complex answer remains just out of reach. Tabby's star stands as a powerful testament to the fact that sometimes the most intriguing discoveries are not the ones that provide answers, but the ones that relentlessly ask better questions, forcing us to broaden our imagination and consider possibilities we had never before dreamed of. But if galactic collisions and stellar oddities challenge our understanding of cosmic structures, then the black hole information paradox strikes at the very heart of physics itself, threatening to unravel our most fundamental laws. It began with one of Stephen Hawking's most brilliant and troubling insights. He realized that black holes are not truly black. Due to quantum effects at the very edge of their event horizons, they should slowly radiate away their mass, emitting what we now call Hawking radiation. This process is so gradual that for a stellar mass black hole, it would take longer than the current age of the universe to evaporate significantly. But given enough time, a black hole could, in theory, completely evaporate, vanishing from existence and leaving behind only a faint bath of this thermal radiation. This is where the paradox begins. Hawking radiation is purely thermal. Its properties are determined only by the black hole's mass, charge, and spin. It contains no other information about what fell in. Every detail, the unique arrangement of atoms that made up a star, the chemical composition of an entire planet, even the specific pages of a book if you were foolish enough to throw one in, all of that information seems to be utterly erased from the universe. This presents a catastrophic problem for quantum mechanics. One of the absolute bedrock principles of quantum theory is the conservation of information. In the quantum world, information is never truly lost. It can be scrambled, diffused, or become hopelessly complex to retrieve. But it must, in principle, be possible to reverse time and reconstruct the original state. If you burn a book, the information isn't gone. It's just transformed into the precise arrangement of atoms in the smoke and ash. If you had a perfect, impossibly powerful computer, you could theoretically reverse the process and reconstruct the book. Hawking's calculations suggested that black holes don't burn the book. They annihilate it from reality, violating unitarity, the mathematical rule that guarantees information preservation. This meant the two pillars of modern physics, general relativity, which describes black holes, and quantum mechanics, were fundamentally incompatible. For decades, this was the status quo, a stalemate known as the black hole information paradox. Physicists were forced to choose. Either Hawking was right and quantum mechanics needed a radical overhaul, or our understanding of black holes was profoundly incomplete. The majority of physicists sided with quantum mechanics, trusting that information must be preserved somehow, and that the fault lay with our classical picture of a black hole. But how, if information can't escape and the black hole vanishes, where does the information go? This launched a decades-long quest for a solution, giving rise to some of the most exotic ideas in theoretical physics. One particularly dramatic proposal is the black hole firewall hypothesis. Imagine carefully falling feet first into a black hole. According to Einstein's general relativity, you should feel nothing special as you cross the event horizon. It is not a solid wall but a point of no return for light and information. The principle of equivalence ensures you would be in free fall. However, quantum mechanics suggests that for information to be preserved, the event horizon cannot be this peaceful. To allow the information about your body to be encoded into the Hawking radiation leaving the black hole, the horizon would have to be a seething, incredibly energetic region, a literal wall of fire that would instantly incinerate you. This resolves the paradox by preventing anything from actually falling in, but it does so by blatantly violating Einstein's principle of equivalence, creating a new conflict between the two theories it was trying to reconcile. A more holistic and widely favored solution comes from the holographic principle, an idea that sounds like it's straight out of science fiction. It proposes that all the information describing a three-dimensional volume of space, like the interior of a black hole, can be entirely encoded on its two-dimensional boundary, the event horizon. Think of it like a hologram where a three-dimensional image is stored on a flat, two-dimensional piece of film. In this view, when matter falls into a black hole, its information isn't lost, it is smeared and imprinted onto the surface of the event horizon. Then, as Hawking radiation is emitted, this radiation subtly carries that information away, like a slow, incredibly complex data transmission. The information is never actually inside the black hole, it's always on the surface and is eventually released back into the universe. The paradox is solved because information is conserved, but it requires us to completely rethink the nature of reality, suggesting that the three-dimensional world we perceive might be a projection of information stored on a distant, two-dimensional surface. The debate is far from settled, but the very struggle to solve this paradox has been incredibly fruitful, forcing physicists to push the boundaries of knowledge and bringing us closer than ever to a potential theory of quantum gravity, a single framework that can finally unite the world of the very large with the world of the very small. Yet, even as we contemplate the grandest cosmic paradoxes, some of the most puzzling mysteries can be found hiding in the tiniest of discrepancies, a lesson perfectly embodied by the decades-long enigma of the pioneer anomaly. In the vast, silent expanse of the outer solar system, far beyond the orbit of Neptune, two robotic pioneers were quietly making history. The Pioneer 10 and 11 spacecraft, launched in the early 1970s, were the first human-built objects to travel through the asteroid belt, conduct close-up observations of Jupiter and Saturn, and then continue on a one-way journey into interstellar space. As they sped toward the stars, teams at NASA meticulously tracked their positions using the Doppler effect, measuring the precise frequency of their radio signals to determine their velocity down to an astonishing accuracy of millimeters per second. And that is when they noticed something was subtly, yet undeniably, wrong. According to every known law of orbital mechanics and gravitational physics, the pull of the sun's gravity on the distant probes should have been causing a very specific, very predictable rate of deceleration. But the pioneers were slowing down just a little bit more than they should have been. It was an almost imperceptible drift, a sunward tug equivalent to a 10 billionth of a gravity on Earth, a force so small it's like the weight of a single grain of sand resting on your hand. Yet, over the course of a year, this minuscule effect would cause a deviation of thousands of miles from their expected positions. For over 2 decades, this anomalous acceleration persisted, a constant, unexplained whisper of physics that didn't quite fit. It was a classic locked room mystery, but the room was the entire solar system, and the suspects were the fundamental laws of the universe. The persistence of the effect immediately launched a frantic search for an explanation, one that split the scientific community into 2 camps. The first and most thrilling possibility was that we had stumbled upon new physics. Perhaps our understanding of gravity itself was incomplete on the largest scales. Maybe Newton's inverse square law needed a tiny modification for extremely weak gravitational fields, a concept proposed in some alternative theories. Other exotic ideas included the influence of unseen dark matter subtly dragging on the probes, or even the mind-bending possibility that the spacecraft were interacting with higher dimensions of space. For a time, the Pioneer anomaly represented a potential crack in the foundation of classical physics, a hint that there was something profound we were missing about how the cosmos works. The second, and ultimately correct, line of inquiry was far more mundane but no less brilliant, a hidden systemic effect. The spacecraft themselves had to be the source. The Pioneer probes were powered by radioisotope thermoelectric generators, or RTG. These nuclear batteries produce electricity from the heat of decaying plutonium, and in doing so, they also produce a lot of waste heat. This heat was dissipated into space through metal fins. The crucial insight was that this heat radiation didn't just vanish, it carried momentum. Every photon of infrared light radiating away from the spacecraft acted like a tiny, microscopic rocket thruster pushing in the opposite direction. For a brief period, this explanation was doubted because early thermal models suggested the effect would be too small. But a painstaking, years-long effort to reconstruct the exact thermal design of the decades-old spacecraft, to map how heat flowed from the RTGs through the craft's body and radiated away from its surface, eventually confirmed it. The radiation was not perfectly symmetric. A slightly greater fraction of this thermal photons were being emitted from the aft end of the spacecraft, the side facing away from the sun and their direction of travel. This created a tiny but continuous net force pushing back against their motion, exactly accounting for the anomalous deceleration. The mystery was solved not by rewriting the laws of physics, but by finally accounting for the subtle physics of a tea kettle effect. The legacy of the Pioneer anomaly, however, is far greater than its solution. It stands as a powerful, humbling lesson in the importance of systematic error and the incredible precision of modern science. It taught astronomers and physicists to become cosmic detectives, to leave no stone unturned, especially the ones right in their own backyard. The rigorous process of eliminating every possible mundane explanation, from the pressure of the solar wind to the leakage of thruster fuel, raised the standard for how we verify our deepest theories. This culture of extreme scrutiny is now directly applied to other modern mysteries, like the precise orbits of other distant probes. It forces us to ask when we see a strange signal, is it a message from the universe or is it just our own equipment whispering? This painstaking attention to detail is what allows us to have confidence when we truly do encounter something that defies explanation, ensuring that when the next great anomaly appears, we will be better prepared to recognize whether it is a flaw in our models or a glimpse of a deeper truth. But this invisible cosmic architecture reaches far beyond our solar neighborhood, woven into the very fabric of galaxies themselves in the form of colossal magnetic fields. We often visualize galaxies as colossal collections of stars, gas, and dark matter bound together by gravity, yet there is another, far more subtle force at work: magnetism. Spiral galaxies like our Milky Way are encased in vast, invisible magnetic fields that stretch for tens of thousands of light years, their lines of force following the graceful curve of the spiral arms. These fields are incredibly weak, millions of times weaker than a common refrigerator magnet, but their sheer scale gives them a profound influence over the cosmos. They can guide the flow of interstellar gas, shape the formation of new stars, and direct the paths of high-energy cosmic rays. The great mystery is not their existence, but their origin and incredible longevity. How does a galaxy build and, more puzzlingly, maintain such an immense and organized magnetic field over billions of years? The leading theory for centuries has been the dynamo effect, a process we see at work on Earth that generates our own planet's magnetic field. It requires three ingredients: a rotating body, a convecting fluid that can conduct electricity, and, crucially, a pre-existing seed magnetic field to get the process started. In a galaxy, the rotating body is the galaxy itself. The convecting fluid is the turbulent, ionized gas that fills the space between stars. As this charged gas moves through the weak seed field, it generates electrical currents. These currents, in turn, amplify the original magnetic field. The rotation of the galaxy then twists and winds these amplified field lines, organizing them into the large-scale patterns we observe. It's a beautiful, self-sustaining cycle, but it presents a monumental chicken-and-egg problem. Where did the initial seed magnetic field come from in the first place? The dynamo theory needs a starting push, but we have no clear source for that first, faint magnetic whisper in the early universe. This puzzle has led to a startling and revolutionary idea. Perhaps these magnetic fields did not grow gradually but were born strong, playing a fundamental role in the very birth of galaxies. Observations from some of our most powerful telescopes, like the ALMA array, are now peering back to when the universe was less than 1 billion years old, and they are finding something astonishing. Some of the earliest, most primordial galaxies already show evidence of well-ordered, large-scale magnetic fields. This is far too early for a classical dynamo to have had time to amplify a weak seed into a coherent field. It suggests that magnetic fields might be a primordial feature of the cosmos, woven into the universe's fabric from its very beginning, perhaps even generated during the inflationary period a fraction of a second after the Big Bang. In this scenario, magnetism wasn't a later addition to galaxies. It was a foundational ingredient that helped gas collapse and cool to form the first structures, actively shaping galactic evolution from the very start. Modern radio telescopes are now creating the first detailed maps of these invisible forces across nearby galaxies, and the patterns they reveal are both beautiful and bewildering. We see magnetic lines perfectly tracing the spiral arms, acting as cosmic rail guides for dense clouds of gas. But in the chaotic, turbulent halos above and below the galactic disks, the fields become complex and frizzed, a sign of immense energy injection from supernova and stellar winds. Perhaps the most stunning finds are the magnetic arms, huge, coherent structures that run parallel to the visible spiral arms, but are sometimes completely offset from them, as if the galaxy has a hidden magnetic skeleton operating independently of its starry body. We simply do not understand the physical mechanisms that can create and maintain such isolated, gigantic magnetic structures. The more we look, the more it becomes clear that magnetism is not a passive side effect of a galaxy's life. It is an active and dynamic player, a fundamental force that has been directing the cosmic show since the beginning, and one whose full script we are only just beginning to read. Yet, even as we map the invisible magnetic architecture of galaxies, a far more fundamental measurement is revealing a deep and growing crack in our standard model of the entire cosmos. For a century, we have known the universe is expanding, but a central goal of modern cosmology has been to pin down the exact rate of that expansion, a number known as the Hubble constant. Determining this value is like finding the most important ruler in the universe, allowing us to measure cosmic distances and piece together the entire history of everything. For decades, astronomers assumed that as our methods improved, different techniques would converge on a single, precise number. Instead, they have done the exact opposite, splitting into two irreconcilable camps and creating a crisis known as the Hubble tension. On one side, we have the traditional cosmic distance ladder, a meticulous step-by-step process that builds out from our local cosmic neighborhood. It starts with precise parallax measurements to nearby stars from missions like Gaia, which act as a foundation. Astronomers then use certain types of stars, like Cepheid variables, as standard candles. These stars have a known intrinsic brightness because their pulse rate is directly tied to their luminosity. The slower the pulse, the brighter they are. By measuring their apparent brightness from Earth, we can calculate their distance with remarkable accuracy. We find these Cepheids in nearby galaxies that also host a special kind of stellar explosion, Type 1a supernova. These supernovae are even brighter standard candles, and by calibrating their peak brightness using the Cepheids in the same galaxy, we can then use them to measure distances to galaxies far across the universe. This entire chain of measurement, meticulously assembled over decades, points to a Hubble constant of about 73 kilometers per second per megaparsec. This means that for every megaparsec, about 3.3 million light-years of distance, a galaxy is moving away from us 73 kilometers per second faster. On the other side of this divide is a completely different approach, one that looks back to the very beginning of the universe. This method uses the cosmic microwave background, the faint afterglow of the Big Bang, as a snapshot of the infant cosmos. By mapping the tiny temperature fluctuations in this ancient light with exquisite precision, as done by the Planck satellite, we can measure the fundamental ingredients of the universe, the amounts of normal matter, and dark energy. We can then run the cosmological model forward in time to predict what the expansion rate should be today. This method is incredibly powerful and self-consistent, but it yields a different answer, approximately 67 kilometers per second per megaparsec. The difference between 73 and 67 might seem small, but in the world of precision cosmology, it is a chasm. The statistical significance of this discrepancy has now grown to between 4 and 5 sigma, meaning there is only a 1 in 100,000 chance that it is a random fluke. This isn't a margin of error, it is a persistent, glaring signal that something in our understanding is fundamentally wrong. The most exciting possibility is that this tension is not an error in measurement, but a sign of new physics beyond our current standard model of cosmology. Perhaps dark energy, the force driving the accelerated expansion, is not a constant as Einstein proposed. Maybe it is dynamic, evolving, and strengthening over the history of the universe. This would mean its repulsive force was different in the past than our models assume, which would change the predicted expansion rate today. Another compelling idea involves the early universe. The Planck measurement relies on a precise count of the particles present in the first moments after the Big Bang. What if there were additional types of relativistic particles, often called dark radiation, zipping around at near light speed? These extra particles would have altered how quickly the early universe expanded, which would subsequently change the sound waves frozen into the cosmic microwave background. Adjusting for this could then bring the early universe's prediction into alignment with the higher expansion rate we see today. There are, of course, more cautious voices who suggest the problem may lie not with the universe but with our measurements. Could there be an unrecognized systematic error in the cosmic distance ladder? Perhaps our understanding of Cepheid variables or the physics of Type 1a supernova is not as rock solid as we believe. Teams are now using new methods, like the subtle geometry of light from distant quasars being warped by gravitational lensing, or the distinct sound wave pattern imprinted on the distribution of galaxies to provide independent checks. So far, these new techniques are only deepening the mystery, often landing in between the two established values or leaning towards one side, but never resolving the conflict. The Hubble tension has become the central problem in cosmology, a puzzle that refuses to be solved with conventional ideas. It forces us to confront the humbling reality that our otherwise incredibly successful model of the universe is missing a crucial piece, and that the true nature of cosmic expansion may be far stranger and more wonderful than we ever imagined. And while the Hubble tension challenges our understanding of the universe's expansion, another profound mystery lies in simply accounting for all the basic stuff it's made of. We are not just missing the dark components, we have somehow lost half of the normal matter. This is known as the missing baryon problem, and it's a cosmic inventory error of epic proportions. Baryons are the particles that make up everything we can see and touch: protons, neutrons, and the atoms they form. This is the stuff of stars, planets, and people. Based on our pristine measurements of the cosmic microwave background, which acts as a detailed receipt from the Big Bang, we know exactly how much of this normal matter should exist in the universe today. But when astronomers add up all the baryons they can actually see in the local universe, all the stars, the glowing gas in galaxies, the hot plasma in galaxy clusters, they come up shockingly short. A staggering 30 to 50% of the ordinary matter that must exist is simply nowhere to be found. For decades, this was a huge embarrassment. How could we possibly lose track of half the atoms in the cosmos? The leading hypothesis pointed to a vast, diffuse cosmic web. The theory of structure formation predicts that dark matter forms an invisible scaffolding throughout the universe, and that ordinary matter is drawn into these filaments, creating a gigantic, interconnected network often called the cosmic web. At the intersections of these filaments, matter collapses to form galaxies and clusters. But the theorists argued that the majority of the missing baryons shouldn't be in these dense knots, but in the filaments themselves, spread over mind-bogglingly vast distances. This material, dubbed the warm-hot intergalactic medium, or WIM, would be incredibly difficult to detect. It's not cold enough to form distinct clouds that absorb light, and not hot and dense enough to glow brightly like a galaxy cluster. It exists in a ghostly state, a thin, million-degree plasma that is so diffuse it hardly interacts with light at all. Finding this faint whisper of matter required a whole new way of observing the universe. The key was to look not for the WIM itself, but for its subtle effect on the brightest beacons in the cosmos. Astronomers used powerful X-ray telescopes like XMM Newton and Chandra to stare at distant quasars, the intensely luminous cores of active galaxies. As the light from these cosmic lighthouses travels across billions of light years to reach us, it passes through these invisible filaments. The theorists predicted that the oxygen atoms in the WIM should be highly ionized, stripped of their electrons, and that these ions would have a very specific absorption signature. It would be like seeing the faint, specific shadow of a nearly transparent ghost against a brilliant light. For years, the search yielded nothing but frustrating upper limits. The signal was too weak, the background too noisy. Then, a breakthrough. By stacking data combining the signals from the light of multiple quasars that had passed through similar cosmic web structures, astronomers finally began to see a faint but statistically significant signal. It was the specific absorption line of highly ionized oxygen, exactly as predicted. This was the first direct evidence that the missing baryons were indeed there, hiding in plain sight in the vast spaces between galaxies. More recent observations have further strengthened the case. The eROSITA X-ray telescope, which is conducting an all-sky survey, has begun to actually see the faint glow of this warm hot gas in the largest filaments, essentially taking a picture of the cosmic web itself. This is a monumental achievement, like finally developing a lens that can see the invisible. Yet, the case is not entirely closed. While these detections are incredibly promising, fully accounting for every last atom is a Herculean task. The densities and temperatures of the WIM vary enormously, and our current telescopes are only sensitive enough to detect the densest and hottest parts of these filaments. There could still be a significant portion of the missing matter in an even more elusive, cooler form that continues to evade our detection. the hunt for the missing baryons is a brilliant example of scientific deduction. We knew the matter had to be there because our fundamental model of the universe demanded it. We theorized where it could be hiding, and then we engineered ever more sensitive tools to prove it. It's a cosmic treasure hunt that is finally paying off, revealing a universe where the spaces between the galaxies are not empty at all, but filled with a tenuous, seething ocean of matter that holds the answer to one of astronomy's most persistent accounting problems. Yet as we piece together the cosmic web and find the missing matter within its filaments, we must also confront the unsettling existence of its polar opposite, vast, hauntingly empty regions where the web has seemingly unraveled. Among these cosmic voids, one stands out not just for its size, but for its profound emptiness, earning it the ominous nickname the Great Nothing. This is the Boötes Void, a spherical region of space so colossal and so barren that it defies our standard models of how the universe arranged itself after the Big Bang. Located about 700 million light-years from Earth in the constellation of Boötes the Herdsman, this void is not a complete vacuum. That would be impossible, but its emptiness is staggering. Imagine a sphere of space 330 million light-years across. Within a volume that immense, our standard cosmology predicts there should be approximately 10,000 galaxies. Instead, astronomers have only found about 60. That means well over 99% of the galaxies that should be there are simply missing. It is a ghost town on a scale so vast it is difficult for the human mind to even comprehend. If the Milky Way were at the center of the Boötes Void, our awareness of other galaxies would not have begun until the 1960s, when telescope technology finally became powerful enough to peer beyond its desolate borders. The existence of such a massive underdense region poses a direct challenge to our understanding of cosmic structure formation. The prevailing model, which includes dark matter and dark energy, does predict that the universe should have a frothy, bubbly structure, a cosmic web of dense clusters and filaments surrounding emptier voids. This is a natural result of gravity pulling matter together over billions of years, leaving behind less dense areas, but the Boötes Void is an extreme outlier. It is far larger and far emptier than our best simulations suggest should be possible. It's as if you baked a loaf of raisin bread and found one region the size of your fist that contained only 2 or 3 raisins, while the rest of the loaf was packed with them. This isn't just a curiosity, it's a potential crisis for cosmology. How could gravity, which works to pull matter together, have created a void of such magnificent nothingness without leaving behind some trace of the matter that must have once been there? Scientists have proposed several theories to explain this great nothing. One compelling idea is that the Boötes Void isn't a single, primordial structure, but the result of a cosmic accident, the merger of several smaller voids. Over the eons, as the universe expanded, the walls between adjacent smaller voids could have thinned and broken, allowing them to flow together into one gigantic empty region. It's a process akin to soap bubbles merging into a larger one. This is a plausible natural explanation, but even this scenario struggles to account for the sheer, profound emptiness observed. The merging process would likely leave behind some debris, a population of galaxies stranded in the emptiness, but the void remains desperately poor. This has led to more exotic proposals that reach back to the universe's very first moments. The theory of cosmic inflation, a period of exponential expansion a fraction of a second after the Big Bang, is a cornerstone of modern cosmology. It explains the overall uniformity of the universe, but it also predicts that quantum fluctuations during this hyper-fast expansion would have been stretched to enormous sizes, seeding the initial density variations that later grew into galaxies and clusters. Perhaps the Boötes Void is the imprint of an exceptionally large negative quantum fluctuation. In this view, the void isn't an accident of later evolution, but a primordial feature woven into the fabric of space-time from the very beginning, a fossilized bubble of less than nothing that inflated into a cavern of breathtaking scale. This would mean its existence was predetermined in the first instance of creation, a permanent scar on the cosmos. There is also a more radical, though less likely, possibility that the void is not entirely empty but filled with something we cannot see. Could it be home to an unprecedented concentration of dark energy, or perhaps a different form of energy field, exerting a repulsive force that prevented galaxies from forming there? Or does its existence hint at something even stranger, like a flaw in the fabric of spacetime itself? The Boötes void stands as a humbling reminder of the limits of our knowledge. It is a colossal absence that speaks volumes, forcing us to question whether our models of the universe's growth are complete, or if we are missing a crucial piece of physics that governs the distribution of everything and nothing in the cosmos. Yet, even as we chart the vast emptiness of cosmic voids, we find that the universe has populated these deserts with some of its most enigmatic and ghostly inhabitants. Drifting through the sparse regions of galaxy clusters, astronomers have discovered a class of objects so faint and so diffuse they challenge the very definition of a galaxy. These are the ultra-diffuse galaxies, or UDG, and they are cosmic paradoxes. Imagine a galaxy the size of our own Milky Way, with its majestic span of 100,000 light-years. Now imagine that instead of containing hundreds of billions of stars, it holds only 1% of that number, perhaps just a single billion stars. That is an ultra-diffuse galaxy. They are immense yet ethereal, sprawling yet ghostly transparent, with so few stars that if you were standing on a planet inside one, the night sky would be nearly black, a stark contrast to our own star-filled Milky Way. For decades, these faint ghosts were simply too dim to be noticed, lost in the glare of brighter galaxies and the fog of Earth's own atmosphere. Their discovery in large numbers is a triumph of modern telescope technology, particularly the Dragonfly telephoto array. This instrument, a network of commercially available telephoto lenses specially modified to reject scattered light, acts like a giant insect's eye, making it exquisitely sensitive to detecting extremely faint, low-surface brightness objects. When pointed at massive galaxy clusters like Coma, Dragonfly didn't just find a few oddballs. It revealed a whole hidden population of these ultra-diffuse galaxies, suggesting they are a common, though previously invisible, part of the cosmic landscape. Their very existence immediately posed a profound question. How does something so large with so little visible matter hold itself together? Gravity from the stars we can see is nowhere near sufficient to prevent such a wispy structure from simply flying apart. The obvious and prevailing answer for decades has been dark matter. The assumption was that these UDGs must be absolutely dominated by it, that each one is embedded within a massive, sprawling halo of dark matter, whose immense gravitational pull provides the necessary glue to keep the few stars in place. This would make them perfect cosmic laboratories, places where the dark matter vastly outweighs the visible, allowing us to study its pure gravitational effects. But the universe, in its infinite capacity for surprise, had a twist in store. While many ultra-diffuse galaxies do seem to be dark matter-rich, a few shocking exceptions have turned this neat explanation on its head. The most famous examples are two UDGs in the NGC 1052 group, nicknamed NGC 1052 DF2 and DF4. Measurements of the motions of their star clusters revealed something that sent shockwaves through the astronomy community. The stars were moving surprisingly slowly, indicating a gravitational pull so weak that it could be accounted for entirely by the visible stars alone. These galaxies appeared to have little to no dark matter whatsoever. This was in many ways more baffling than the galaxies that were full of it. If dark matter is the invisible scaffolding that all galaxies form within, how did these galaxies form without it? It would be like finding a massive, fully constructed building with no foundation, no steel frame, and no support beams, just floating in midair. This discovery triggered a fierce and ongoing scientific debate. skeptics question the distance measurements to these galaxies, arguing that if they were actually much closer to us than believed, their apparent size and mass would shrink, potentially resolving the anomaly. However, subsequent, more precise observations have largely confirmed the initial startling results, strengthening the case that these are indeed galaxies lacking their dark matter component. This presents a monumental challenge to our models of galaxy formation. How do you make a galaxy without dark matter? One compelling theory suggests they are failed galaxies. Perhaps they began life as normal galaxies in the early universe, but their gas, the raw material for forming stars, was violently stripped away by the gravitational tides of a larger neighbor. This would leave behind a dark matter halo that was also stripped and dispersed, and a population of stars that had already formed, now left to drift as a massive, diffuse relic. Another, more dramatic theory proposes that these dark matter-free galaxies are the product of a cosmic cataclysm. During a violent collision and merger of two large galaxies, a massive splash of gas and stars could have been ejected. This ejected material, suddenly free from the gravitational grip of its original dark matter halo, could then have coalesced under its own gravity to form a new galaxy made purely of visible matter. In this scenario, these UDGs aren't failed galaxies, but newborn ones, forged from the debris of a galactic accident. The existence of both dark matter-rich and dark matter-poor ultra-diffuse galaxies forces us to confront the incredible diversity of galactic evolution. They demonstrate that the relationship between dark matter and visible matter is not as simple and rigid as we once thought. These ghostly giants are not merely astronomical curiosities, they are critical stress tests for our theories. The dark matter-rich ones challenge our understanding of how dark matter condenses and behaves, while the dark matter-poor ones challenge the foundational idea that you even need dark matter to form a galaxy in the first place. They represent two sides of the same mysterious coin, each posing a different but equally profound question about the nature of the universe's hidden mass and the forces that sculpt the galaxies we see. But just when we think we understand the limits of what can travel through the cosmos, the universe delivers another paradox, this time involving particles of such staggering energy that their very existence seems to break the rules of interstellar travel. These are ultra-high-energy cosmic rays, and they carry more punch than any particle we can create on Earth, with energies millions of times greater than those produced by the Large Hadron Collider. Each one is a single subatomic particle, a proton, or the nucleus of an atom, hurtling through space at nearly the speed of light, carrying the kinetic energy of a well-thrown baseball. Their origin is one of the great mysteries of astrophysics, but their journey is governed by a law that should make them impossible to see from Earth, a theoretical barrier known as the Greisen-Zatseping-Kuzmin limit, or the GZK cutoff. This limit isn't a wall in space, it's a fundamental consequence of the universe not being empty. Space is filled with the faint, relic photons of the cosmic microwave background, the afterglow of the Big Bang. For a proton traveling at these insane energies, this cosmic background radiation is no longer a harmless whisper of light. Instead, these photons appear like a dense fog of high-energy gamma rays due to the proton's incredible speed. According to well-tested principles of particle physics, when such an ultra-high-energy proton collides with one of these background photons, the interaction should be catastrophic. The proton would lose a tremendous amount of its energy by creating new particles, a process that would rapidly sap its strength over distances of about 150 million light-years. This means that any cosmic ray with energy beyond the GZK limit should only be able to reach us from sources within our local galactic neighborhood. From beyond that local volume, the cosmic microwave background should act as a cosmic sieve, filtering out these extreme particles and creating a sharp cutoff in the energy spectrum we observe. The paradox is that this isn't what we see at all. Giant observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah are designed to detect these rare events. They don't catch the particles directly, but instead observe the massive cascades of secondary particles, air showers, that are created when the cosmic ray slams into our atmosphere. Over decades, these facilities have recorded dozens of events with energies clearly beyond the GZK limit. These particles are here, and they have traveled from far beyond our local group of galaxies. It's as if marathon runners arrived at the finish line not only unexhausted but bursting with more energy than they started with, having somehow sprinted through a field of quicks and without slowing down. This presents a thrilling dilemma that forces us to question our understanding on multiple fronts. The first and most obvious question is about the particles themselves. Have we misunderstood the fundamental physics of how protons interact with light? Could there be some exotic new particle making this journey that doesn't obey the same rules? Some theories have proposed that these could be strangelets, hypothetical nuggets of strange quark matter, or even magnetic monopoles, all of which would interact very differently with the cosmic background radiation. However, these ideas remain highly speculative without any experimental evidence. The second, and perhaps more compelling, possibility is that our understanding of the physics is correct, but our knowledge of the sources is wrong. The GZK calculation assumes these particles are simple protons. If they are instead heavier atomic nuclei, like iron, the story changes. Heavier nuclei have a higher energy threshold before the GZK effect kicks in, potentially allowing them to travel farther. But this explanation has its own problems, as it's incredibly difficult to accelerate a heavy nucleus to such phenomenal speeds without it being torn apart in the process. This leads to the third and most profound implication of the GZK paradox. It might be pointing us to sources of acceleration so powerful and so efficient that they defy our current models of astrophysical engines. To accelerate a particle to these energies requires conditions far more extreme than a supernova explosion. The suspected accelerators, called zevatrons because they can reach energies of 1 zeta electron volt, are thought to be the most violent events in the universe. Prime candidates include active galactic nuclei, where matter spiraling into a supermassive black hole generates immense jets of plasma or gamma-ray bursts, the most powerful explosions since the Big Bang. But even these phenomenal events are pushed to their theoretical limits to explain the highest energy cosmic rays we detect. The paradox suggests that these engines might be even more powerful and efficient than we thought, or that there is an entirely new class of cosmic accelerator out there that we have yet to discover. The mystery is compounded by the fact that these ultra-high-energy cosmic rays are so rare only a few arrive per square kilometer per century, and they don't point directly back to their source. Their paths are bent and twisted by the magnetic fields that fill interstellar and intergalactic space, making the task of tracing them back to their origin like trying to find the source of a single drop of rain in a hurricane. The GZK paradox is therefore a multi-layered puzzle, a conflict between impeccable theory and stubborn observation that challenges our grasp of particle physics, our models of cosmic accelerators, and our understanding of the empty space between galaxies. It is a stark reminder that the universe is capable of generating forces and particles that push at the very edges of what we believe is possible. But if the vast, ghostly forms of ultra-diffuse galaxies represent one extreme of galactic structure, the dynamic, high-energy flows within more active galaxies represent another, showcasing a hidden life cycle of matter that powers the birth of new stars and the death of old ones. Within the bustling disks of spiral galaxies like our own, a continuous and violent cycle is at work, an engine of creation and destruction that astronomers call galactic fountains. Imagine the scene after a massive star, many times the size of our Sun, reaches the end of its brief, brilliant life and explodes as a supernova. The cataclysm does more than just scatter heavy elements across space. It acts like a cosmic piston, violently ejecting enormous bubbles of million-degree gas and energized particles out of the thin galactic plane at speeds of hundreds of kilometers per second. This material, having escaped the gravitational pull of the disk, soars high into the galaxy's extended halo, a region thousands of light-years above the starry spiral arms. From this lofty vantage point, the hot gas begins to cool, condensing into denser clouds that eventually succumb to the galaxy's gravity. Like a celestial waterfall, this cooled material then comes raining back down onto the disk, providing a fresh infusion of fuel for the next generation of stars. This magnificent loop, an upward blast of energy followed by a life-giving rain, is a fundamental regulatory mechanism for a galaxy's evolution, controlling the rate of star formation by recycling its most precious resource, gas. For decades, our theoretical models of this process were elegantly simple, portraying these fountains as relatively orderly, localized cycles. A supernova goes off, it blows a bubble of gas up, the gas cools and falls back down nearby, and the process repeats. This neat picture suggested that galaxies could efficiently recycle their own material, creating a self-sustaining ecosystem. However, recent observations from powerful telescopes like the Hubble Space Telescope and various X-ray observatories have completely shattered this simplified view, revealing a system of far greater complexity and scale than anyone imagined. We now see that the gas doesn't just make a short, neat loop. Instead, it is often launched on epic journeys, traveling tens of thousands of light-years away from its origin point before eventually falling back, meaning the gas that rains down on one part of the galaxy may have come from a supernova explosion in a completely different spiral arm. Furthermore, the material doesn't descend as a uniform shower. It comes down in massive, discrete clumps and filaments, which astronomers have poetically termed high-velocity clouds. These are not gentle drizzles but torrential downpours of condensing gas, and their sheer mass and velocity present a whole new set of puzzles. The most significant challenge for modelers is accounting for the incredible mixing that occurs during this cycle. When the supernova-heated gas is launched into the halo, it doesn't travel as an isolated bubble. It churns and mixes with the halo's own pre-existing gas, a medium that is itself poorly understood. This interaction strips material from the fountain flow, heats the surrounding halo gas, and creates a turbulent interface that is devilishly difficult to simulate with any real accuracy. The models that come closest to replicating the observed chaos require immense computing power and still struggle to predict the final fate of the ejected material. How much of it is lost to the halo forever? How much is thoroughly mixed with other elements, and how much actually makes it back to the disk in a form that is usable for forming new stars? These are fundamental questions that remain largely unanswered. This complexity has profound implications for the life story of a galaxy. The galactic fountain is not just a recycler, it is a primary distributor of the heavy elements forged in stellar cores and supernova explosions. As the fountain gas circulates, it seeds the entire galaxy with these metals, effectively polluting the pristine hydrogen and helium with the building blocks of planets and life. The efficiency of this process directly influences the chemical evolution of the galaxy, determining how quickly subsequent generations of stars become enriched with these elements. If the fountain flows are more efficient than we thought, they could spread metals faster and farther. If they are less efficient and more material is lost into the intergalactic void, it could mean that galaxies slowly bleed out their star-forming fuel over billions of years, a gradual exhausting of their primary resource. The recently discovered Fermi Bubbles emanating from our own galactic center are a spectacular, large-scale example of this fountain process operating at a truly monumental level, demonstrating that these flows can shape a galaxy on the grandest of scales. The humble galactic fountain, once thought to be a simple, closed loop, is now revealed as a chaotic, galaxy-wide circulatory system, a vital and messy lifeblood that we are only just beginning to understand. Yet, even as we map the complex circulatory systems of mature galaxies, we must rewind the cosmic clock back to the very first minutes of existence, to a puzzle embedded in the creation of the simplest elements. In the fiery crucible of the Big Bang, during a brief window known as Big Bang nucleosynthesis, the universe was hot and dense enough to forge the first atomic nuclei from a primordial soup of protons and neutrons. In a matter of minutes, this process produced almost all the hydrogen and helium in the cosmos today, along with trace amounts of two other light elements, deuterium and lithium. For the most part, our theoretical predictions for these abundances, based on our well-tested understanding of nuclear physics, match the observed values in the oldest, most pristine corners of the universe with stunning accuracy. This agreement is a cornerstone of the Big Bang theory, but there is one glaring, persistent exception, a single elemental discrepancy that has stubbornly refused to be resolved for over 3 decades. It is known as the cosmological lithium problem. The problem is one of simple accounting. Our models of Big Bang nucleosynthesis, which have been refined to an incredible degree of precision, predict that for every 10 billion hydrogen atoms in the universe, there should be about 4 or 5 atoms of lithium-7, the stable isotope of lithium. To test this prediction, astronomers look to the oldest stars in our galaxy, the so-called population Roman II stars that formed from gas that had been minimally polluted by later generations of supernova. These ancient stellar relics are our time capsules, preserving the chemical composition of the early universe. When we measure the lithium abundance in their atmospheres, we consistently find only about 1/3 of the predicted amount. There is simply not enough lithium-7 in these old stars. It's as if the universe's original recipe called for a specific ingredient, but when we check the oldest pantry, we find most of it is missing. The persistence of this problem is deeply frustrating because it exists at the intersection of two otherwise incredibly successful fields of physics. Our understanding of nuclear cross-sections, the probabilities of particles interacting, is exquisitely precise, honed by decades of particle accelerator experiments here on Earth. And our standard model of cosmology, which provides the conditions for the early universe, has been overwhelmingly validated by observations of the cosmic microwave background. Yet when these two impeccably tested fields are combined to predict the amount of lithium, they are off by a factor of 3. This isn't a small statistical fluctuation. It's a significant and robust discrepancy that has survived every new observation and theoretical refinement. It suggests a fundamental gap in our knowledge, a missing piece of physics that operated only in that unique, hyper-dense, hyper-hot environment of the first few minutes. Scientists have pursued two broad paths to solve this mystery. The first path questions whether our understanding of the nuclear reactions themselves is complete. Perhaps there are unknown or poorly measured reaction rates in the complex chain that leads to lithium-7. For instance, the nucleus beryllium-7 is a crucial stepping stone. It decays into lithium-7 with a half-life of about 53 days. Could this nucleus have been destroyed by neutrons or other particles through a reaction channel we haven't fully accounted for? Some physicists have proposed that beryllium-7 might have been transmuted by hypothetical exotic particles, like certain types of dark matter that were abundant in the early universe. If a dark matter particle interacted with and destroyed beryllium-7 before it could decay, it would effectively erase the lithium that was supposed to form. While this is a compelling idea, no definitive evidence for such a specific dark matter interaction has been found. The second, and more radical, path suggests that the initial conditions of the Big Bang were different than we assume. The predicted abundance of lithium is exquisitely sensitive to the density of baryons, or normal matter, in the early universe. Our best measure of this density comes from the Planck satellite's map of the cosmic microwave background, which is a snapshot from 380,000 years after the Big Bang. The lithium problem forces us to ask, could something have happened between the first 3 minutes and those first 380,000 years that altered the baryon density in a way that Planck wouldn't see? It seems unlikely, as the two epochs are powerfully linked. Another fascinating proposal involves the potential existence of magnetic fields in the very early universe. If strong primordial magnetic fields were present during nucleosynthesis, they could have influenced the reaction rates between charged particles, potentially suppressing the formation of lithium-7. This remains a speculative but active area of research. There is also the possibility that the answer lies not in the creation of lithium, but in its subsequent destruction. Perhaps the ancient stars we use as cosmic probes are not the pristine vessels we believe them to be. Could these old stars have internal processes that slowly destroy lithium over their multi-billion-year lifetimes, while some surface lithium can be diluted through mixing with the lithium-poor interior of a star? Detailed stellar models suggest this effect is not nearly sufficient to account for the entire discrepancy. The lithium problem stands as a quiet but profound anomaly, a small crack in the otherwise solid edifice of the Big Bang theory. It reminds us that even our most successful models are approximations of a deeper reality, and that the universe's first few minutes may still hold secrets about fundamental physics that we have yet to uncover. And yet, even as we find ourselves pulled by the Great Attractor and surrounded by the intricate flows of our galactic fountain, we must confront a possibility that places us not at the center of the universe, but in the center of a colossal nothing. What if our entire local group of galaxies, including the Milky Way, is not in an average region of space, but is instead floating in the heart of a vast cosmic void? This isn't a philosophical thought experiment. It's a serious scientific hypothesis known as the KBC void, named for the astronomers Ryan Keenan, Amy Barger, and Lennox Cowie who proposed it. The evidence suggests we may reside inside an immense spherical underdensity of matter nearly 2 billion light-years across, a bubble of relative emptiness in the grand cosmic web. If true, this would be a discovery of profound significance, challenging one of the most cherished principles in cosmology, the idea that on a large enough scale, the universe is homogeneous and looks the same in every direction, a concept known as the cosmological principle. This principle is the foundation upon which virtually all of modern cosmology is built. It allows us to assume that the laws of physics are the same everywhere and that our local observations can be fairly applied to the universe at large. The existence of a void as immense as the one proposed, where the density of galaxies is up to 50% lower than the cosmic average, would force a dramatic re-evaluation of this assumption. It would mean our vantage point is not typical at all, but is instead a biased and unusually empty one. The KBC void is not just another empty region like the Boötes void, it is defined by its concentric shells. The proposal suggests that as we look out from our position, the density of galaxies increases with distance, creating a layered structure where we are at the center of the lowest density zone, surrounded by a shell of higher density, which is then surrounded by the true cosmic average. Mapping this structure is incredibly difficult, like trying to discern the shape of a building you are inside of by only looking at the walls. This is where the Hubble tension, that nagging discrepancy in the universe's expansion rate, re-enters the story with a potential and elegant solution. The local measurements, which use Cepheid variables and supernova, are all calibrated within our cosmic neighborhood, a volume of space that would be entirely inside this proposed void. In an underdense region like the KBC void, the gravitational landscape is different. There is less matter pulling on galaxies from all sides, which means the expansion of space within the void would be less impeded by gravity's restraining pull. As a result, space inside the void would be expanding slightly faster than the global average. Our local measurements would therefore be accurately measuring this faster local expansion rate, but we would be mistakenly assuming it applies to the entire universe. Meanwhile, the Planck satellite's measurement from the cosmic microwave background provides a global average expansion rate, one that smooths over all the dense clusters and empty voids. In this scenario, both measurements could be correct. They are simply measuring the expansion rate in two different environments, one local and fast, the other global and slower. The tension wouldn't be an error, but a revelation about our unusual address in the cosmos. The implications of this idea are staggering, extending far beyond just the Hubble constant. If we are in a void, it would affect our measurements of dark energy, as the perceived acceleration of the universe could be influenced by our underdense environment. It could even offer an alternative explanation for the axis of evil alignment in the cosmic microwave background. The void could gravitationally lens the ancient light, subtly distorting its patterns to create the illusion of a preferred direction. However, the KBC void hypothesis is far from settled science. Its existence is hotly debated because it pushes the limits of what is considered a plausible structure under the standard model of cosmology. Some large-scale surveys seem to show an underdensity in our local universe, while others suggest the galaxy distribution is more uniform. The next generation of galaxy redshift surveys, like those conducted with the Dark Energy Spectroscopic Instrument, are designed to map the universe in 3 dimensions with unprecedented precision. These projects will essentially conduct a cosmic census, counting galaxies across vast volumes of space and finally allowing us to determine, once and for all, if our home is in a typical suburban neighborhood of the cosmos, or if we are living in a grand and isolated countryside, looking out at a universe that is far denser and more active than our own quiet corner. And yet, even as we consider the possibility that our entire local universe might be sitting inside a vast void, we are confronted with a mystery that suggests something is pulling on everything from far, far beyond. Imagine tracing the paths of thousands of galaxy clusters, the most massive gravitationally bound structures in the universe, each containing thousands of galaxies. You would expect their motions to be random, a chaotic dance governed by the local tug of nearby superclusters and the overall expansion of space. But that is not what a team of astronomers found when they studied the subtle patterns in the cosmic microwave background. They discovered something they called dark flow, a perplexing, coordinated motion where these immense clusters appear to be streaming in a preferred direction at astonishing speeds of over 600 miles per second, a motion that cannot be explained by any known gravitational force within our observable universe. This discovery was made by looking at the hottest gas within these clusters, which casts a specific shadow on the cosmic microwave background through a process called the kinematic Sunyaev-Zeldovich effect. This incredibly subtle distortion allows scientists to measure the gas's velocity relative to the overall expansion of the universe. The results were as shocking as they were controversial. The clusters weren't just moving, they were all moving together like leaves caught in a vast, unseen cosmic current. The sheer scale of this motion is what makes it so baffling. The gravitational pull from all the visible and dark matter we can see should only influence structures out to a certain distance. Dark flow, however, appears to be coherent across billions of light years, implying the source of this immense pull lies far beyond the horizon of our observable universe. This immediately leads to one of the most dramatic and mind-bending proposals in all of modern cosmology. That dark flow could be the first empirical evidence for the multiverse. The theory is that the gravitational influence of other universes, residing in a vast multiverse beyond our own cosmic bubble, could be tugging on the matter within our universe. If these other universes are close enough in a higher dimensional space, their gravity could, in theory, leak across and provide the extra pull needed to explain this coordinated motion. It's a staggering idea that we might be detecting the ghostly hand of another reality entirely, a neighboring cosmos exerting its influence on our own. Of course, such an extraordinary claim requires extraordinary evidence, and the dark flow effect itself remains hotly debated within the cosmological community. Skeptics have proposed more conventional explanations, though even these challenge our understanding. One possibility is that our universe is not as homogeneous as the cosmological principle assumes. Perhaps there are pre-inflationary inhomogeneities, massive, primordial density variations that were imprinted on the fabric of space-time before the rapid expansion of inflation began. These could create gravitational potentials so deep and vast that they pull on galaxy clusters across unimaginable distances. Another, more technical argument suggests that the measured effect could be an artifact of the way we process the cosmic microwave background data, a subtle systematic error that mimics a coherent flow. The debate is far from settled. Subsequent studies have both supported and refuted the original findings, and the required precision to measure such a faint signal is at the very limit of our technological capabilities. The true nature of dark flow, whether it is a revolutionary glimpse into a grander multiverse or a complex illusion born from our own incomplete data, remains one of the most provocative open questions in science. It challenges the very notion of our cosmic isolation, teasing the possibility that our universe is not a solitary island, but one of many in a far vaster and stranger metaphysical sea, all connected by forces we are only just beginning to sense. Now let's journey from the vast, flowing currents of the cosmos to our own planetary home, to a time when the sun hung in the sky as a much dimmer, cooler orb. Scientists call this the faint young sun paradox, and it presents a deceptively simple problem with profoundly complex implications for the story of life itself. Our sun, like all stars of its type, has brightened over its lifetime. Billions of years ago, during the Archean Eon when life first emerged on Earth, our star was only about 70% as luminous as it is today. According to every basic climate model we have, that reduction in solar energy should have been more than enough to keep Earth in a deep global freeze. The entire planet should have been a snowball, locked in ice from pole to pole, with average temperatures far below the freezing point of water. And yet, the geological record tells a completely different story. We have clear evidence from some of the oldest rocks on Earth, such as pillow basalts that can only form underwater and zircon crystals that hint at liquid water erosion, that our planet had widespread oceans of liquid water as far back as 4 billion years ago. This isn't just a minor discrepancy, it's a direct conflict between astrophysics and geology. If the models say the world should have been frozen, but the rocks say it was wet and temperate, then our understanding of planetary climate or stellar evolution must be missing a crucial piece. The most intuitive and long-standing solution to this paradox points to the planet's ancient atmosphere. Today, carbon dioxide is a greenhouse gas of great concern, but billions of years ago, it may have been the hero that saved the world from an eternal ice age. The idea is that a much thicker atmosphere, brimming with CO2 and possibly methane, could have created a powerful greenhouse effect, trapping enough of the sun's faint heat to keep the oceans liquid. This theory is supported by models that show it is physically possible, but it faces a major hurdle when we look for supporting evidence in the geological record. When we analyze ancient soils and sedimentary rocks from the Archean era, the chemical proxies for atmospheric CO2 levels don't point to concentrations high enough to do the job alone. The amounts we find are significant, but they fall short of what the climate models require to offset the faint sun's weakness. This has forced scientists to consider other, more potent greenhouse gases that could have been partners in this planetary warming. Methane is a prime candidate. Molecule for molecule, methane is a far more effective greenhouse gas than carbon dioxide. It's possible that early life itself, specifically primitive microbes called methanogens, could have been generating vast quantities of methane, creating a biological blanket that helped warm the planet. Another intriguing possibility is that the early atmosphere lacked its modern-day thermostat. Today, oxygen enables the formation of an ozone layer that shields nitrous oxide from being broken down by sunlight. Nitrous oxide is another powerful greenhouse gas, and without an ozone layer, it might have built up to much higher concentrations in the Archean sky. There's also the fascinating, though more speculative, idea of an ammonia haze. Ammonia is an excellent greenhouse gas, and though it is easily broken down by ultraviolet light, some theories suggest it could have been protected within a layer of atmospheric organic haze or inside icy cloud particles, allowing it to persist and contribute to the warming. Beyond the composition of the air, other factors unique to a young Earth may have played a critical role. The planet itself looked very different. There were no vast continents of light-colored, reflective rock. Instead, the land was likely limited to smaller, darker volcanic islands that would have absorbed more solar heat rather than reflecting it back into space. The oceans, too, may have been darker, lacking the reflective whitecaps and plankton that help cool the modern seas, and instead perhaps being stained by dissolved minerals from intense volcanic activity. Even the sun's own behavior might have been a factor. A young sun, though fainter in total output, was likely far more magnetically active, producing more intense flares and a stronger solar wind. This could have compressed Earth's magnetic field, potentially leading to more energetic particles reaching the upper atmosphere and creating warming nitrous oxides. Or it might have simply provided a different quality of light that interacted with the ancient atmosphere in ways we don't fully understand. Despite all these compelling ideas, a complete and universally accepted solution to the faint young sun paradox remains elusive. Each proposal has its own weaknesses. High greenhouse gas levels might leave different chemical fingerprints than those we've found. A darker, less reflective planet might not have been enough on its own. This lingering uncertainty is what makes the paradox so powerful. It forces us to admit that we may not fully understand the delicate and complex interplay of factors that make a planet habitable. It suggests that Earth's climate stability over billions of years, which allowed life to not just emerge but to thrive and evolve, may have been the result of a fortunate and intricate balancing act between geology, astronomy, and perhaps even biology itself. The paradox is a humbling reminder that our planet's past holds deep secrets about resilience and change, secrets that may be crucial to understanding not only our own history but the potential for life on other worlds orbiting other, fainter young stars. While the faint young sun paradox asks us to reimagine our own planet's ancient climate, a storm of an entirely different order has been raging for decades on a world a billion kilometers away, presenting a geometric mystery that defies the very nature of chaos. At Saturn's North Pole, a feature unlike any other in the solar system dominates the atmosphere, a perfect, persistent hexagon. This is not a solid structure, but a colossal jet stream, a six-sided wave of wind tearing through the upper clouds at over 300 miles per hour, with a central hurricane large enough to swallow the entire Earth. The most baffling aspect is its endurance. Earth's weather patterns change hourly, and even Jupiter's great red spot, while centuries old, is gradually shrinking and changing shape. Yet Saturn's hexagon has remained geometrically rigid, a precise six-sided figure, since it was first glimpsed by the Voyager probes in the early 1980s and then studied in stunning detail by the Cassini spacecraft decades later. This is a stability that atmospheric scientists simply cannot explain. The turbulent, churning gases of a giant planet's atmosphere should have long since shredded and scrambled any such precise pattern into a featureless blur. The quest to understand this phenomenon has moved from the rings of Saturn to the confines of physics laboratories here on Earth. Scientists use rotating tanks of fluid to simulate the atmospheres of giant planets, as the Coriolis effect created by a spinning planet is the dominant force shaping their weather. When they set these tanks in motion, they can create all sorts of fascinating patterns: waves, ovals, and turbulent eddies. But creating a stable hexagon has proven incredibly difficult. The key seems to lie in the speed differential between different layers of the atmosphere. Imagine pouring a very thin stream of milk into a cup of coffee and then gently stirring it. You might see a temporary polygon form in the swirling liquid before it dissipates. Saturn's atmosphere may be acting on a planetary scale, where the deep internal winds of the planet shear against the upper, visible cloud decks, creating a steep gradient in wind speed that can, under very specific conditions, generate and then lock in a standing wave pattern with exactly 6 sides. But why 6? The mathematics of fluid dynamics offers a fascinating clue. In a rotating fluid, the most stable patterns are not random. They often settle into specific wave numbers, which describe how many peaks and troughs a wave has as it wraps around a circle. For the specific conditions believed to exist in Saturn's polar atmosphere, its rotation rate, wind shear, and viscosity, the mathematics suggests that a wave number of 6 is exceptionally stable. It's a natural resonance, much like how blowing across the top of a glass bottle produces a specific musical note. Saturn's North Pole seems to be singing a note of exactly 6 sides. This doesn't fully solve the mystery, however. It just translates it into a new language. We still don't know the precise planetary properties that tune this atmospheric instrument so perfectly, nor do we understand the energy source that has maintained this resonant note with such unwavering fidelity for over 40 Earth years and likely much longer. The hexagon is more than just a pretty shape. It acts as a massive barrier containing different atmospheric conditions within its walls. The air inside the hexagonal jet stream is notably different from the air outside, almost like a vast 6-sided petri dish isolating a unique meteorological experiment. During Saturn's long polar winter, which lasts for over 15 Earth years, the entire region was plunged into darkness, shrouding the hexagon from view. When the sun finally rose again, the Cassini spacecraft was there to watch, revealing that the hexagon was not only still there, but it appeared to act as a catalyst for the formation of enormous, swirling hazes of particles, painting the inside of the structure with mysterious golden hues. This suggests the pattern is not just a surface feature, but a deep-seated structure that extends hundreds of kilometers down into the planet's atmosphere, influencing chemistry and physics far below the cloud tops we can see. Saturn's hexagon stands as a majestic and humbling reminder that the laws of physics can create order on a scale we are only beginning to appreciate, a stable geometric symphony playing out in the violent winds of a distant giant, whose secrets are still locked deep within its swirling, 6-sided heart. Yet, even as we ponder the geometric perfection of a storm on a world within our own solar system, we are reminded that some of the most profound mysteries are not bound to any star at all, but are instead silent travelers passing through the vast darkness between them. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint, fast-moving object that immediately stood out from the millions of others in their survey. Its trajectory was not a closed ellipse around the sun, but a stark, open-ended hyperbola. This was no ordinary asteroid or comet from our own solar system. It was the first confirmed visitor from interstellar space, an ambassador from another star. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first, and the message it carried was one of profound and enduring mystery. The initial analysis painted a picture of a truly bizarre object. Based on its changing brightness, it was determined to be highly elongated, shaped like a pancake or a cigar, tumbling end over end through space. Its color was a deep, dull red, similar to many organic, rich objects in the outer solar system. But the biggest surprise came as astronomers continued to track its path. As Oumuamua sped away from the sun, something was wrong with its trajectory. The precise measurements showed it was not just coasting under the influence of gravity alone. It was experiencing a tiny but persistent additional acceleration, a push that was subtly altering its course. This kind of non-gravitational acceleration is common for comets. As a comet's icy surface is heated by the sun, It vents gas and dust, creating a visible coma and tail that act like a natural rocket engine. The crucial and utterly baffling detail was that Oumuamua showed no such activity. Every dedicated search for even a faint wisp of gas or dust around it came up completely empty. It was accelerating as if it were outgassing, but without any of the visible signs that should accompany such a process. This discrepancy launched a frantic and fascinating scientific debate that continues to this day, centered on one simple question: what was pushing it? The most natural explanations all point to some form of outgassing, but of a very exotic kind. One leading hypothesis suggests that Oumuamua could be a fractal-like aggregate of dust, what some scientists call a dust bunny, with such a low density that the gentle pressure of sunlight itself, called radiation pressure, could have provided the necessary push. Another compelling idea is that it was a chunk of solid molecular hydrogen. In the cold, dense cores of giant molecular clouds, such hydrogen icebergs could theoretically form. The beauty of this theory is that when warmed by the sun, solid hydrogen would sublimate directly from a solid to a gas without leaving behind any reflective dust, creating a perfectly invisible jet. However, the survival of such a fragile object over millions of years' journey through interstellar space is highly questionable. Other theories propose that the acceleration could be due to the object's unusual shape. A tumbling, pancake-like body would have a complex interaction with solar radiation that could, in theory, produce a small net force. Or perhaps it was ejecting large, sand-sized particles that were too sparse to create a visible coma but numerous enough to provide a measurable thrust. Each of these natural explanations is clever, but each also faces significant challenges. The hydrogen iceberg model requires a very specific and rare birth environment. The radiation pressure model requires an object of incredibly low density, unlike anything we see in our own solar system. Oumuamua seemed to be just at the edge of what our current understanding of solar system formation allows, a statistical outlier that pushed the boundaries of every natural category. It was this very uniqueness that led to the most famous and most speculative hypothesis that Oumuamua was not a natural object at all, but a piece of alien technology. Astronomer Avi Loeb proposed that its unusual acceleration and strange shape could be consistent with a light sail, a thin, reflective sheet designed to be pushed by starlight for propulsion. In this scenario, the non-gravitational acceleration would be exactly what you'd expect from such a structure catching the solar photons. Its flattened shape would be ideal for a sail, and its lack of outgassing or a visible coma would be because it wasn't a comet at all, but a manufactured object, perhaps a derelict probe or a fragment of a larger vessel. This idea, while sensational, was never presented as the only possible answer, but rather as a legitimate possibility that should be considered given the failure of more conventional models to fully explain the observations. The true nature of Oumuamua remains an open case, a single data point of an entirely new class of object. Its fleeting visit and our inability to study it more closely with dedicated missions means we may never know its true secret. But its legacy is immense. It proved that interstellar objects are common visitors to our solar system, opening up a whole new field of astronomy. It forced us to confront the limitations of our knowledge and to expand our imagination about what is possible in the great diversity of planetary systems. Oumuamua was a messenger, and its message was a humbling one, that the universe is filled with forms and phenomena we have yet to dream of, and that sometimes the most extraordinary discoveries are the ones that slip away before we can fully understand them. Journey now from the lonely voyage of an interstellar visitor to the very heart of our own galaxy, where an entirely different kind of mystery is blazing in a wavelength of light invisible to our eyes. At the center of the Milky Way, where stars are packed so tightly they create a perpetual daylight, and the supermassive black hole Sagittarius, a star, holds court, there is a light that should not be there. It is not a light you can see. It is a persistent, diffuse glow of high-energy gamma rays, an excess of radiation that blankets the galactic center with no obvious source. Astronomers call it the galactic center excess, and it is a cosmic puzzle that has stubbornly resisted explanation for over a decade, forcing us to choose between a surprising new population of stars or a revolutionary glimpse into the nature of dark matter itself. This mysterious light was first uncovered not by an optical telescope, but by a champion of high-energy astronomy, the Fermi Gamma Ray Space Telescope. As scientists meticulously mapped the gamma-ray sky, they carefully subtracted all the known sources of this powerful radiation. The frenzied pulsars, the remnants of supernova explosions, the interactions of cosmic rays with interstellar gas. When all that was removed, a residual glow remained, a hum of excess energy concentrated within the central few thousand light-years of the galaxy. It was as if they had silenced a roaring stadium crowd only to hear a faint, unchanging, and omnipresent chorus coming from everywhere at once. The glow itself has a very specific energy signature, a spectrum that peaks at around 2 giga-electronvolts, and it is remarkably symmetrical, fading away smoothly as you move out from the galactic center. This specific profile is the crucial clue that every proposed theory must explain. From the moment of its discovery, the most tantalizing hypothesis was that this glow was the long-sought-after sign of dark matter annihilation. The theory is elegant. If dark matter is made of weakly interacting massive particles or WIMP, then these particles should be their own antimatter counterparts. When two WIMP collide, they would annihilate each other in a flash of energy, producing a shower of standard model particles, including gamma rays at very specific energies. The galactic center is the perfect place to look for such a signal because it is predicted to have the highest density of dark matter in the entire galaxy, a vast, dense cloud that would make these collisions far more frequent. The observed spectrum of the galactic center excess, with its particular peak, matches surprisingly well with the predicted gamma-ray signature from the annihilation of WIMP with a mass around 30 to 40 times that of a proton. For a time, it seemed like we might be on the verge of one of the greatest discoveries in science, finally catching dark matter in the act. However, as the data improved and analyzers became more sophisticated, problems with this elegant story began to emerge. The spatial distribution of the glow turned out to be the biggest stumbling block. The excess emission isn't just a smooth, round blob as most simple dark matter halo models would predict. Instead, it appears slightly more elongated, and its shape seems to trace not the invisible dark matter, but the visible stellar population of the galactic bulge, the dense collection of ancient stars that surrounds the center. This is a critical detail. If the gamma rays were truly from dark matter, their glow should align with the predicted shape of the dark matter cloud, which is typically more spherical. The fact that it seems to follow the stars suggests the source might be something made of ordinary matter after all. This realization launched a vigorous search for an astrophysical culprit, and the leading candidate is a fascinating one, a vast, unseen army of millisecond pulsars. Imagine the corpses of massive stars spun up to incredible speeds by siphoning material from a companion star. These millisecond pulsars are neutron stars that rotate hundreds of times per second, sweeping powerful beams of radiation across space like cosmic lighthouses. They are known to emit gamma rays, and a population of thousands of them, too faint to be detected individually, could collectively create the exact diffuse glow we observe. Their combined light would naturally trace the distribution of stars in the bulge, neatly solving the spatial distribution problem. Recent analyzers have provided tantalizing support for this idea. Sophisticated statistical methods have been applied to the Fermi data, searching for the telltale flicker of point sources hidden within the smooth excess. Some studies claim to have found evidence for such a population, suggesting the glow might not be perfectly smooth but could be made up of the combined light of countless unresolved points. Yet the debate is far from settled. Other teams argue that the evidence for point sources is not statistically significant and that the emission remains resolutely smooth. Furthermore, the millisecond pulsar theory has its own challenges. Forming such an immense population of these objects in the galactic center requires a specific and prolific history of stellar evolution and binary interactions that we have not yet independently confirmed. We are left in a stalemate, a classic scientific standoff where the evidence is compelling for both sides but conclusive for neither. The galactic center excess is a reminder that the universe often presents us with ambiguous clues, forcing us to improve our tools and sharpen our questions. Whether it is the faint applause from a hidden crowd of stellar remnants or the first whisper of particles that make up the majority of matter in the universe, this unexplained glow at the heart of our galaxy represents a frontier of discovery, a puzzle whose solution will undoubtedly reshape our understanding of the cosmos, no matter which answer finally proves to be true. But our journey into the heart of galactic mysteries now takes us to the very observation that started it all, the discovery that first forced us to confront the reality of an invisible universe. It's a puzzle rooted in a simple, predictable law of orbital motion, one that we can observe in our own solar system. When planets orbit the Sun, those closer in, like Mercury, whip around at incredible speeds, while the outer worlds, like Neptune, move at a much more leisurely pace. This is a direct consequence of gravity's pull weakening with distance. The Sun contains over 99% of the solar system's mass, so its gravitational grip is all that matters. As you move further out, that grip weakens and objects must move slower to maintain a stable orbit. For over 3 centuries, since the time of Newton and Kepler, we assumed this same rule would apply on a grander scale to entire galaxies. The visible mass of a galaxy, its stars and glowing gas clouds, is concentrated in the bright central bulge and disk. Therefore, stars orbiting near the edge of the galaxy, far from this central mass, should be moving much more slowly than those closer in. If you were to graph this, plotting a star's orbital speed against its distance from the galactic center, you would expect to see a curve that rises steeply and then falls away just as steeply, a signature known as a Keplerian decline. In the 1970s, astronomer Vera Rubin set out to test this fundamental assumption by measuring the rotation curves of spiral galaxies. Using sensitive spectrographs, she and her colleague Kent Ford meticulously tracked the Doppler shift of light from stars and gas clouds at different distances from the centers of these galaxies. The results were not just surprising, they were earth-shattering. Instead of seeing the expected decline in speed for the outer stars, the rotation curves remained flat. Stars and gas clouds tens of thousands of light-years out in the galactic boonies were orbiting at virtually the same breakneck speed as those near the bright inner core. It was as if every car on a vast, sprawling highway, regardless of whether it was near downtown or out in the remote countryside, was traveling at exactly 60 miles per hour. This made no sense according to the laws of gravity and the amount of visible matter. The only possible explanation was that there had to be a tremendous amount of unseen mass far beyond the visible edge of the galaxy, providing the extra gravitational pull to keep those outer stars whipping around so fast. This invisible mass, which does not emit or absorb light, became what we now call dark matter. The flat rotation curve is perhaps the most direct and compelling evidence we have for its existence, a ghostly gravitational hand guiding the motion of every star in a galaxy. Faced with this paradigm-shifting discovery, a small but dedicated group of physicists pursued a radically different path. Instead of inventing a new, invisible form of matter, they asked a profound question: what if we are wrong not about what's there, but about the rules themselves? This line of thinking gave birth to modified Newtonian dynamics, or MUND, proposed by physicist Mordechai Milgrom in the 1980s. MUND suggests that Newton's laws of gravity, which work perfectly well in our solar system, break down in environments of extremely weak acceleration, like the faint gravitational fields at the outer edges of galaxies. Milgrom's idea was elegant in its simplicity. He proposed a new constant of nature, a specific tiny acceleration threshold. Above this threshold, gravity behaves exactly as Newton and later Einstein described. But below it, gravity becomes stronger following a different mathematical rule. This modification perfectly explains the flat rotation curves without needing a single particle of dark matter. The gravity in the outskirts of a galaxy becomes just strong enough to hold onto those fast-moving stars, creating the observed flat curve. For certain galaxies, particularly isolated dwarf galaxies, Man's predictions were strikingly accurate, often more so than early dark matter simulations. However, as our observational power grew, Man began to encounter serious and ultimately fatal problems. Its greatest failure came from the world of galaxy clusters. When two massive clusters of galaxies collide, we can observe the aftermath. The most famous example is the Bullet Cluster. In this cosmic wreck, the visible matter in the form of hot, X-ray emitting gas was slowed down and stuck in the middle of the collision due to friction. But the vast majority of the mass, as mapped by the effect of gravitational lensing where the cluster's gravity bends light from background galaxies, had sailed right through the collision and was now located in two regions far away from the visible gas. This was a direct visualization of the difference between normal matter and dark matter. The normal matter interacted and got stuck. The dark matter did not interact and kept going. For mind, which modifies the force of gravity itself and does not invoke any separate collisionless matter, this observation is nearly impossible to explain. The gravity and thus the lensing effect should be strongest where the most visible matter is located, which is in the central gas cloud, but the lensing showed the mass was somewhere else entirely. This was a direct, empirical demonstration that there is a form of matter that is not only dark but also behaves differently from normal matter during collisions. No modification of gravity alone can account for this separation. You need two different types of stuff. Furthermore, the precise details of the cosmic microwave background, the afterglow of the Big Bang, provide a cosmic recipe for the universe's composition. The specific pattern of fluctuations in this ancient light can only be reproduced if the universe contains about 5 times more dark matter than normal matter. A universe governed by mind alone cannot replicate this pattern. While some proponents have tried to create relativistic versions of mind that incorporate additional fields to mimic dark matter in these extreme cases, these theories become increasingly complex and ad hoc, losing the elegant simplicity that made mind appealing in the first place. They often end up requiring their own forms of hidden matter or energy fields, making them seem less like a simple alternative and more like a more complicated version of the standard model with different names for the unknowns. The preponderance of evidence, from colliding galaxy clusters to the sound waves of the early universe, strongly favors the existence of dark matter as a physical substance. The rotation curve problem was our first clue, a single thread that, when pulled, began to unravel the fabric of our understanding, revealing a universe dominated not by what we see, but by what we cannot. Leaving behind the grand, invisible architecture of dark matter, we find that some of the universe's most stunning mysteries are painted across the sky in vivid, geometric detail, a truth perfectly embodied by one of the most uniquely structured objects ever discovered. In the constellation Monoceros, the unicorn, a dying star has not blossomed into a typical, chaotic planetary nebula. Instead, it has sculpted its final farewell into a shape of breathtaking, almost artificial precision, the Red Rectangle Nebula. This bipolar nebula is a profound cosmic anomaly, a celestial structure so geometrically regular and so rich in unexplained spectroscopic phenomena that it has captivated and confounded astronomers since its discovery. At first glance, especially in early images, it appears exactly as its name suggests, a vivid, red, rectangular frame. But higher resolution observations from the Hubble Space Telescope reveal this is an incredible oversimplification. The rectangle is actually a complex ladder-like structure, a series of precise, evenly spaced rungs connecting two opposing cones of ejected material, forming a perfect, if spooky, X shape in the sky. This is not the sort of chaotic, explosive death throes we expect from a star. It looks engineered as if a cosmic architect drafted blueprints for stellar demise. This astonishing symmetry is the nebula's first great mystery. How can a star, in its final, inherently violent act of shedding its outer layers, create something so orderly? The prevailing theory points to a central dense disk of dust and gas, perhaps surrounding a close binary star system. The idea is that as the dying star expels material, this dense disk severely constricts the outflow, funneling it into two opposing jets or cones above and below the disk. The latter rungs are thought to be waves of material like ripples on a pond, ejected in periodic episodes from the star system and made visible as they expand into the cones. This creates the stunning effect of a cosmic escalator to nowhere, a structure that implies a rhythm and a regularity to a process we typically think of as uncontrollable and explosive. But the geometry, as bizarre as it is only half the story. The true, deeper mystery of the red rectangle lies in its name and its light. The nebula emits a profound crimson glow, but this is not the typical red light of excited hydrogen gas that tints many emission nebulae. When astronomers broke its light down into a spectrum, they found something they had never seen before, a series of sharp, equally spaced emission bands in the red part of the spectrum. These bands, which became known as extended red emission or ERE, had no known origin. They did not match the spectral signature of any known atom or molecule. It was as if the nebula was broadcasting on a frequency no one could understand, using an element or a compound that was not on our periodic table. For a time, this was so puzzling that some even jokingly referred to the unknown substance as redrectanglium. The hunt to identify the source of this mysterious glow led scientists down a fascinating path into the world of complex carbon chemistry. The current leading hypothesis is that we are witnessing the faint, collective glow of a specific type of large organic molecule. The prime suspects are polycyclic aromatic hydrocarbons, or PAHS complex, flat molecules made of linked rings of carbon and hydrogen atoms. Think of them as tiny, interstellar snowflakes or fragments of soot. When these molecules are illuminated by the intense ultraviolet light from the central star, they can fluoresce, emitting light at very specific wavelengths that could account for the strange bands. Another compelling candidate is a new form of carbon-based nanoparticle, sometimes called hydrogenated amorphous carbon grains. These are essentially tiny, frozen droplets of tar, and their proposed fluorescence properties also match the observations remarkably well. This explanation, while compelling, is far from settled. The precise physical process that makes these particles fluoresce with such a distinct signature is not fully understood, and creating these conditions in a laboratory to confirm the theory has proven incredibly difficult. The red rectangle, therefore, is more than just a pretty shape. It is a crucial natural laboratory for studying the formation and behavior of complex organic molecules in space. These are the very building blocks of life, and understanding how they form and interact with starlight in environments like this has profound implications for astrobiology. The nebula's unique combination of precise geometry and unexplained chemistry makes it a true one-of-a-kind object. It stands as a majestic and humbling reminder that even in death, a star can create structures of exquisite beauty and profound mystery, challenging us to unravel the complex physics of dust and light that governs the final chapter of a sun's life. Now, let's shift our focus from the grand, sculpted forms of nebulae to the most delicate of cosmic fingerprints, a phenomenon that requires us to read between the lines of light itself. To uncover it, we must turn our gaze to the most brilliant beacons in the distant universe, quasars. These are the intensely luminous cores of galaxies, powered by supermassive black holes feasting on unimaginable quantities of matter. Their light travels for billions of years to reach us, and on that epic journey, it passes through every shred of gas and dust in its path. When astronomers break this ancient light into a spectrum, they don't see a clean, continuous rainbow. Instead, they find the light has been carved up, etched with a stunningly complex series of hundreds, sometimes thousands, of dark absorption lines, all crowding together in a specific part of the spectrum. This thicket of lines is known as the Lyman alpha forest, and it is one of the most powerful yet puzzling tools we have for mapping the invisible architecture of the cosmos. Each one of those tiny lines is a cosmic road sign, a specific fingerprint left by a single cloud of neutral hydrogen gas. The signature is based on a fundamental property of the hydrogen atom. When an electron in a hydrogen atom drops from its first excited state down to its ground state, it emits a photon with a very specific wavelength which we call Lyman alpha light. The reverse is also true. A photon of that exact wavelength can be absorbed by a neutral hydrogen atom, exciting its electron. As the light from a distant quasar journeys through space, it passes through countless clouds of hydrogen. Each cloud, depending on its redshift, a measure of how much the universe has expanded since the light passed through it, absorbs light at a slightly different wavelength. The result is a beautiful barcode stamped across the quasar's spectrum, where the position of each line tells us the distance to that specific hydrogen cloud. By reading this barcode, astronomers can construct a stunningly detailed three-dimensional map of the cosmic web, tracing the vast filamentary structures of matter that stretch between galaxies. The Lyman alpha forest is arguably our single most important probe of the large-scale structure of the universe, revealing the hidden skeleton upon which galaxies are built. Yet, for all its utility as a map, the forest itself is the source of a deep and persistent mystery. The sheer number of these lines, the incredible abundance of these hydrogen clouds, presents a serious challenge to our simulations of structure formation. The clouds are not cold and dense. They are warm, tenuous, and widely distributed throughout intergalactic space. Our models struggle to explain how such a vast quantity of gas was heated to its observed temperature and then distributed in just the right way to produce the precise forest we see. The physics of how energy from the ultraviolet background radiation of galaxies and quasars filters through and heats this intergalactic medium is fiendishly complex. When cosmologists run their most sophisticated supercomputer simulations, they often find a forest that is either too sparse or too dense compared to the real thing. The trees in their digital forest don't quite match the spacing and strength of the lines we observe in actual quasar spectra. This discrepancy points to a gap in our understanding of feedback, the process by which energy from stars and black holes influences their surroundings. Perhaps galactic winds driven by supernova or quasar activity are more efficient at ejecting gas and distributing it into the voids than we have calculated. Or maybe our models are missing a key source of heating that keeps the gas in this specific warm state, preventing it from collapsing into denser clouds or dissipating entirely. The Lyman alpha forest is more than just a map. It is a precise diagnostic tool, a cosmic thermometer and density gauge for the vast spaces between galaxies. Its very structure holds clues to the history of energy production in the universe, from the first stars to the most violent quasars. Each absorption line is a message in a bottle from a specific time and place, and we are still learning the language needed to read the full story it tells about the evolution of the cosmic web itself. But if the Lyman alpha forest reveals the delicate filamentary structure of the cosmic web, then the very existence of the galaxies within that web presents a grander, more dynamic puzzle of cosmic equilibrium. Every galaxy is a battlefield, a continuous struggle between two opposing forces, the drive to create and the imperative to destroy. On one side, gravity works tirelessly to pull gas together, cooling it and compressing it until it ignites into brilliant new stars. This process injects a colossal amount of energy back into the system, ultraviolet radiation that heats the gas, stellar winds that push it away, and eventually supernova explosions that blast it out into the void. This counterforce is known as feedback, and it is the essential regulatory mechanism that prevents a galaxy from either burning through all its fuel in a brief, furious burst or from failing to form stars at all. The most fascinating mystery in modern astrophysics is how galaxies achieve a near-perfect, self-regulating balance between these two opposing processes, maintaining a simmering, sustainable rate of star formation over billions of years. This delicate dance is known as the galactic energy budget, and our attempts to balance its books have revealed significant and puzzling shortfalls. The most dramatic example of this feedback is found in supermassive black holes, which act as the ultimate galactic governors. When a black hole at the center of a galaxy actively feeds, it can transform into a quasar, launching jets of plasma and radiation at near light speed. These jets can travel for hundreds of thousands of light years, inflating enormous bubbles in the surrounding intergalactic gas and pumping tremendous energy into the galactic halo. This process is so effective that it can literally shut down star formation across an entire galaxy by heating and dispersing the cold gas required to make new stars. This is a negative feedback loop of breathtaking power. Too much star formation leads to more gas falling into the black hole, which activates it, which then shuts down the star formation. It's a cosmic thermostat. However, in many galaxies, especially older elliptical galaxies, we see evidence of past quasar activity that should have permanently shut down all star formation. Yet, these galaxies often show signs of recent, small bursts of stellar birth. Our models struggle to explain how enough cold gas can somehow return to the galaxy or avoid being heated by these past eruptions, suggesting our understanding of this feedback cycle is incomplete. On the smaller but no less important scale of individual stars, another energy crisis emerges. When we calculate the total energy poured into a galaxy's interstellar medium by all its supernova explosions and stellar winds, we find that it is often not enough to account for the observed motions and temperature of the gas. There is a missing energy source, a deficit in our accounting that becomes especially apparent in smaller, dimmer galaxies. Supernova are powerful, but they are isolated events. The energy they release tends to dissipate quickly in localized hot bubbles rather than uniformly heating the entire galactic environment. This has led to the search for other, more distributed and continuous sources of energy. One leading candidate is the combined effect of countless smaller stars. The steady, gentle pressure of starlight itself, particularly from massive stars, can exert a surprising influence over vast clouds of dust and gas. Furthermore, the cosmic rays generated by supernova, extremely high-energy protons and atomic nuclei, may play a far greater role than previously thought. These particles can travel much farther than supernova shockwaves, depositing their energy gradually across a wider volume of space and helping to drive large-scale galactic winds. But even when we add up all these potential sources, the models often still fall short, pointing to the possibility that we are still missing a key piece of physics in our understanding of how energy is transferred from stars to their surrounding environment. This failure of our simulations to capture the true complexity of galactic ecosystems is perhaps the most humbling aspect of the energy balance problem. The interstellar medium is not a uniform gas. It is a multiphase, turbulent froth where hot, ionized gas, warm atomic clouds, and cold, dense molecular filaments all coexist and interact in a chaotic dance. Energy is not transferred in a simple, linear fashion. It cascades down from large scales to small scales through a process called turbulent dissipation, much like how a large whirlpool in an ocean breaks down into smaller and smaller eddies until the energy is finally converted into heat. Capturing this incredibly complex process in a computer simulation is a monumental challenge. Our models must simulate the entire galaxy while also trying to account for physics on the scale of individual stars and even planets, a range of scales that is computationally impossible to bridge with current technology. Because of this, astrophysicists are forced to use simplified approximations for these small-scale processes, and it is almost certain that these approximations are smoothing over critical details about how energy is truly injected and distributed. The galactic energy balance is not a simple equation. It is a symphony of chaos, a self-regulating system whose intricate rhythms we are only just beginning to hear, and whose most important instrumentalists may still be hidden from our view. And yet, after mapping the delicate energy balance within individual galaxies, we arrive at a puzzle on the grandest scale of cosmic structure, a question not about what is there, but about what is conspicuously absent. According to our most sophisticated computer simulations of how dark matter and gas evolve over billions of years, the universe should be populated by absolute behemoths, galaxies so enormous and bright they would dwarf even the largest known galaxies today. These predicted cosmic giants residing at the hearts of the most massive clusters should be truly staggering, containing many times more stars than anything we have ever observed. Yet when we look out into the real universe with our most powerful telescopes, these predicted titans are nowhere to be found. The very brightest cluster galaxies and the central galaxies in large groups, while still impressively large, consistently fall short of the colossal sizes and luminosities our theories demand. It's as if a cosmic rule, a universal zoning law, has prevented these giants from growing to their full potential, and the prime suspect in this case of the missing giants is one of the most energetic forces in the cosmos, a process we call AGN feedback. To understand this, we must first look at the very engine of a galaxy's growth, its supply of cold gas. Galaxies grow by accreting fresh, cold gas from the vast filamentary web of dark matter that connects them. This gas is the raw fuel for star formation. As it flows into a galaxy's gravitational well, it cools, condenses, and eventually ignites into new stars. In the early universe, particularly at the dense centers of what would become massive galaxy clusters, this process should have been incredibly efficient. Vast rivers of cold gas should have funneled into these central galaxies, fueling an almost unchecked frenzy of star birth that would have created the universe's missing giants. The fact that this did not happen points to a powerful regulatory mechanism, a cosmic thermostat that somehow shut off this fuel supply before the galaxy could grow too large. For a long time, the energy from supernova explosions was considered the main candidate for this job, but it quickly became clear that even the combined might of countless dying stars was not nearly powerful enough to counteract the gravitational pull drawing gas into these deep potential wells. This is where the supermassive black hole enters the story, not as a passive monster, but as an active and dominant governor. Almost every large galaxy has one of these black holes at its center, and when they actively feed on surrounding gas, they transform into what we call an active galactic nucleus, or AN. This feeding process is anything but tidy. As matter spirals inward at incredible speeds, it heats up, generating intense friction and magnetic fields that can launch colossal jets of plasma and radiation out from the black hole's poles at nearly the speed of light. Simultaneously, powerful winds of hot gas can be blown outward in all directions. This is the essence of AGN feedback. It is a monumental release of energy that pushes back against the infalling gas, effectively fighting gravity itself. The energy output from a single, actively feeding supermassive black hole can outshine its entire host galaxy, and more importantly, can heat the surrounding gas reservoir to such incredibly high temperatures that it can no longer cool down and collapse to form stars. The black hole effectively shuts off its own fuel supply and prevents the galaxy from growing any further. The true brilliance of this system is its self-regulating nature. It creates a feedback loop of breathtaking precision. When a lot of cold gas flows into the galactic center, it does two things. It fuels a burst of star formation, and it also feeds the central black hole. As the black hole gorges itself, it becomes active and erupts, ejecting energy that heats the gas and halts both the star formation and its own accretion. Once the eruption subsides, the gas can slowly cool again, and the cycle can start over. This seesawing process prevents the galaxy from either consuming all its fuel in one go or from growing without any limits. However, while this elegant model explains why we don't see the predicted giants, it also presents a new set of profound mysteries. The devil is in the details, and our simulations have historically struggled to get these details right. They often have to artificially tune the efficiency of this feedback to match observations, because the actual physics of how a black hole's energy couples to the surrounding gas is incredibly complex and occurs on scales far smaller than our simulations can typically resolve. This is where the new era of multi-messenger astronomy is revolutionizing our understanding. We are no longer limited to observing these events in just one type of light. By combining data from traditional telescopes across the electromagnetic spectrum with observations of gravitational waves, neutrinos, and cosmic rays, we are beginning to see the full picture of how AGN feedback operates. For instance, studying the correlation between gravitational wave events from merging black holes and the observed properties of their host galaxies could tell us about the role mergers play in triggering AGN activity. Observations of neutrinos, which are ghostly particles that travel unimpeded across the universe, could point directly back to the most violent and obscured environments near active black holes, revealing the engine room of the feedback process. Each new messenger provides a different piece of the puzzle, helping us to move beyond simple tuned models and toward a true, fundamental understanding of how these cosmic giants are kept in check. The mystery of the universe's missing giants is therefore a driving force in modern astrophysics, a clue that has led us to uncover one of the most important relationships in the cosmos, the intimate and often violent dance between a galaxy and the dark heart at its center. And so our journey through 30 of the cosmos's greatest puzzles comes to a close, yet the true takeaway is not a set of answers, but a profound appreciation for the vast landscape of questions that still lies before us. From the ghostly tug of the Great Attractor to the silent, mathematical perfection of Saturn's hexagon, each phenomenon we've explored is a powerful testament to a simple, humbling truth. The more we learn about the universe, the more we discover how much we have yet to understand. These are not mere gaps in a map waiting to be filled. They are glaring signposts pointing toward entirely new continents of physics, realms of reality where our current laws and theories simply break down and a new, deeper understanding must be forged. The existence of dark matter and dark energy, the strange behavior of Tabby's star, the paradoxical whispers of the WOW signal, these are not failures of science but its very engine. They represent the thrilling frontier where curiosity meets contradiction, and where the next great revolution in human thought is waiting to be born. It is on this frontier that the future of discovery is being written, and the potential for groundbreaking Nobel Prize-winning breakthroughs has never been greater. The scientist who finally identifies the true particle nature of dark matter will undoubtedly claim physics' highest honor. The team that reconciles the Hubble tension might not only resolve a crisis in cosmology, but could unveil a new property of dark energy or a flaw in Einstein's relativity. The researcher who devises a convincing solution to the black hole information paradox could very well be laying the groundwork for the long-sought theory of everything. These mysteries are not academic exercises. They are the grand challenges of our time, puzzles that demand new technologies, new generations of brilliant minds, and a relentless, collaborative spirit of inquiry that stretches across the globe and even beyond our planet. Every anomalous data point, every unexplained observation, is a potential thread that, when pulled, could unravel our current model of the universe and reveal a breathtaking new tapestry of reality woven from principles we have not yet dared to imagine. This is the enduring invitation of astronomy, a call to embrace the unknown and to find wonder not in certainty, but in the beautiful, bewildering complexity of a cosmos that forever refuses to be fully known. The universe is not a puzzle to be solved, but an infinite story to be explored, with each chapter revealing deeper layers of mystery. We want to hear which of these enigmas captured your imagination most. Was it the haunting possibility of the wow signal, the violent elegance of galactic cannibalism, or the existential dread of the great nothing? Let us know in the comments below which phenomenon you find most fascinating and why. If you enjoyed this deep dive into the edges of knowledge, be sure to subscribe and hit the notification bell so you don't miss our next journey into the mysteries of space, time, and reality itself. The cosmos is filled with secrets, and together we can continue